Hello, hello, hello. Good morning. That was not anywhere near as energetic as I wanted. How about you? Do you think they could do more energy?
They definitely can.
Come on. Cheer. Hello. Good morning. You think they'd know how to take a cue by this point in time? Actually, this is kind of what your talk's about, isn't it?
Well, yes.
A little bit.
Yeah. I guess so, yes.
How was DConf, Attila?
Amazing as usual. I missed the first hour of it because I was doing agent stuff,
Right.
even though it was free beer.
That's actually unusual for you. You skipped free beer to play with AI.
Yep, that's how much I'm into it.
The world's changing and I don't like it.
You're not the only one.
All right, so before we kick off, I'll do the usual reminder, lightning talks. We got 4 slotted in today. I'd like to have another one if possible. Come on, you guys can think of something surely. But tomorrow we only have 1 talk, so we definitely need more talks for that. So put your brains down, do whatever you do to think of something, whatever. Just come up to me if you've got a lightning talk and we'll do it. Otherwise, let's get this show on the road. Attila.
Thanks. I have a bunch of slides. I'm going to try to go quickly, and just feel free to talk to me later because there's way more slides I want to put in this talk, but I didn't because it was already, too long. Anyway, the idea is that I hate waiting, and some of you will know that I think 200 milliseconds is way too much time to do anything for a computer because it's a ridiculous number of cycles, and 2 seconds to wait for my unit test to run is also ridiculously long. I hate it. It just drives me nuts. And, do I even have to compile the code and link it to actually get the result of my tests? I remember one DConf, I joked, I wouldn't mind if my unit tests ran at compile time because it's basically verifying my code anyway, so what's the point? So that got me thinking about using CTFE to run the unit tests. Most of the time, my unit tests are pure anyway and don't need I/O, so why not? And that's been percolating for a while. And the goal is to have the minimal edit to unit test latency. So I finish editing, tell me if I've broken something or not. I barely care, especially if it's an OK and nothing has failed. I don't really need anything except to know that the tests have actually run. Only if they failed, you actually need an error message to know exactly how and what failed. So that's the idea. And how do we get there? And then I was a big Lisp guy back in the day, and I used Emacs. And in Lisp, you always have a REPL, which is interpreted. And there's this idea that if you want things to go faster, then you can compile it. At the time, I didn't know what that meant. But essentially, it's just a bytecode compiler that does it on the fly. And then the interpreter could interface with that so that if you're calling a function over and over again, it'll be way faster than the interpreter. And back in the 90s, this made a huge difference. And Emacs is basically a Lisp VM that's pre-built with editing functions. That's essentially what that program is, and nearly an operating system, as some people like to call it. And so I thought, well, how about maybe bytecode for D? Will that help me with this edit cycle? Instead of compiling and linking the code, because linking always takes a bunch of time and it's a bottleneck. People have been trying to write linkers that do things in parallel for ages. I tried to do an idea years ago. It just doesn't work. There might be a new one, but basically it's a bottleneck and it's very annoying. So that's the idea. And so I wanted to implement a D backend by taking the DMD front end because all 3 compilers share the front end anyway. There is no other front end that can actually parse the whole of D properly. So the idea is take the DMD front end, parse and do semantic analysis, and now I have an AST. I can take that AST, feed it to different backends. Normally, we feed it to either the DMD CodeGen backend, but also LLVM or the GCC ones. And then, do a new one that's based on that. And you write a visitor, and there's a bunch of different statement kinds and 71 expressions, and apparently 26 statements. You do this over and over again, and there you go. And when dinosaurs roamed the Earth, this is a picture from last year, by the way, because things in the airspace have moved so fast that it might as well have been when dinosaurs roamed the Earth. And I tried this a while back, maybe 2 or 3 years, write me a DMD backend, and AI just refused to. It did one AST node and went, and now you do the rest yourself. I'm like, no, you do it. And it went, no. Computer says no. And I could write code okay-ish, but it couldn't write a lot of code at once, and it would refuse to, like I just said. And yeah, one ASC node at a time. So typing things into ChatGPT and trying to paste them back was slow, and it was nearly just as annoying as doing it yourself. Not quite, but it just wasn't feasible to even attempt this. But since December, we've got agents and models that can, and so now I decided to tackle this again. Like I was saying, we have autonomous agents now that can write a lot of code at once, and it can do it well, for the most part. Not like before. And write me a backend, make no mistakes, should work. It doesn't quite. You can't one-shot it. There are lessons to be had here. And Dennis had the same idea with WASM, and I actually need to take his branch and put it in my benchmark so I can benchmark that backend as well. And Robert talked about it yesterday, so a compiler daemon, etc. I've not got that far, so the idea is just to time different backends to see which one will do better, because there's no way to know a priori which one will, except to try it in real code, because if you compile to bytecode, then you're going to have to take that time to compile, and then it'll probably be faster to execute than interpret, but which one wins, I don't know, nobody does. And it probably depends on the project as well, because it depends on how those unit tests were written. And so I wanted to have competing backends and agents write it. And part of the goal was faster CTFE as well, because if I had a bytecode backend, and Dennis even mentioned this too, what if we use this for CTFE instead of what we have? I think that SDC even uses LLVM JIT to do its CTFE exactly for that. And I think Clang as well for const in C++ has a similar idea. And like I said before, what about running tests at compile time, essentially? And CTFE is already an alternative D backend, to put it that way. It's a thing that executes D, but it's not compile D. And how hard could it be to basically say, can I have a CTFE backend that I can use and benchmark against other things? And it turns out, not really that hard. It's nearly just one function call, say deinterpret, and then there you go, it does. And you can run it really easily. An agent can do this in minutes. And I have a backend that does the CTFE thing. And to achieve CTFE parity, by which I mean to write a new backend from scratch that does exactly the same things that CTFE does, is surprisingly easy. It does not take that much, because CTFE has a bunch of limitations, which means it's not full D. It can't do I/O, it can't do lots of things, which you wouldn't want it to anyway. It's supposed to be a compile time. And I just told it, basically, write a backend that can compete with CTFE, and it can run some example code easily, so simple code that I wrote by myself with some for loops and whatever. But it can't run real projects, and there's multiple reasons for that. And the backends I have is, so I have one that just calls the CTFE engine in DMD, and then I wanted to do a bytecode VM, like I said, but AI ended up convincing me that maybe a tree-walking interpreter is a good idea, because, again, it depends if it's computationally complex or not. If it's not, then you might be able to interpret before the bytecode compiler was finishing compiling. And AI also suggested intermediate representation, which I might toy with, also because that means we could have an SSAIR that could enable a few things like isolated, but we'll see. And then I have to compare it to regular compiled code, because if it's not faster, then what's the point? So if I typed up test, how long does that take to compile and link and then run? And then I started thinking about REPL. That would be cool to have a D REPL. Martin Novak already did one. What it does is it compiles the D code and then links it into a shared library and loads it and keeps doing that over and over again. And can we do better than that? Because obviously that means compiling the code, and it takes a little bit of a while. So every time you type something, it'll take hundreds of milliseconds at least. I was going to do a demo about this, but there's a lightning talk, so I'm going to leave it for that, so I'll show the REPL off then. And then to compare fairly, you need to measure only what happens after parsing and semantic analysis, because if you run dub test, then first the compiler parses, does SEMA, and then does code gen and linking. So you need to take that amount of time away. So what happens if I just parse and semantic analyze and then feed it to the code gen and link and run? All of it put together, because that's going to be your latency when you're actually editing code. And then I wrote a common backend interface, literally an interface in OOP, because that means I can select which backend at runtime. I don't see any other way of doing it. This is literally what dynamic dispatch is for. I wrote a backend called CTFE that just calls the CTFE engine. And then I wrote a backend called System Linker because you have to turn the code-gen code into something executable somehow. So it's using whatever linkers on the system. In my case, mold, because it's the fastest one. And then feed it into different backends, and then time that. This turned out to be harder than that slide seems to suggest, for multiple reasons. So that's what the benchmark thing looks like, measuring the minimum amount of time it took, the median, how many tests were run, because I don't trust the backends, right? Like, how many tests did you find and run, because how do I know you're actually running tests? It's really easy to get a test binary to pass. You just go return 0. Your code is good, brilliant, but I don't know. And so I was comparing all of them. There's also an LLVM JIT thing there that I was playing about with, but that was a pain and didn't really work. So there's a few things that I learned along the way. Some of them had to do with D, some of them had to do with me. And this is the first thing here is to do with D. So when DMD does semantic analysis, it modifies the AST nodes, which I found out because the AI told me. And that meant I couldn't just do what I was doing, and it was very annoying. Also, DMD cogen does the same thing. And so taking that front end, taking the AST and sending it to backends didn't quite work because the cogen would be modifying it as I was sending it somewhere else. And then I considered serializing the state of the compiler to disk, but then I realized that actually I don't need to do that. I just fork. And then I have a copy of the process, and they talk to each other, but that ended up being a bunch of problems too. And templates were great because, DMD was made to be a batch compiler, and it made sense. Why wouldn't it? But when you're trying to do what I was doing and running unit tests, you're taking the same code, parse it once, and then I'm feeding it to 4 different backends. One of them was doing cogen, and then the template code, the compiler has to figure out which module it actually emits the binaries to, and it wasn't doing it right. And so I ended up having linker errors because there was template code that things were referencing that weren't actually in there. And so I ended up creating a fake module that I called the lightning rod, where all the template code would end up so that everything would link. So I'd import all the phobos once, and then emit all the templates, put it in here, and then no linker errors. But that was also really slow. And the famous don't make mistakes. I wanted to run a real project, so I picked one of mine, Serialed, which is about serialization in D, because I figured it was small enough and simple enough that it wouldn't be that hard. Yes, it is, it turns out. And I went, look, get this thing to run. And they did. The agents ended up making it run. But when I looked at the code, it wasn't good. When the cat is away, the mice will play, and I wasn't looking at the code, so the agents did whatever they wanted to do. And what they ended up doing to get over the hurdle I put in front of them, which is run serialed unit tests, was essentially this. Recognizing the code by name, and then doing special casing it. Because it was the easiest way to finish the task, and I wasn't even looking anyway, so it was like, it can't run anything else unless it keeps, recognizing patterns over and over again. At this point, I went, right, it needs to call, libc, for instance. I need FFI. Why didn't I consider this before? Yeah, the test passed, but nothing was actually being interpreted. And so, right, I need FFI. I need to call libc at the very least, or Phobos, the runtime, et cetera. And then if you have a dub project, that might depend on other system libraries. What do you do then? TTFE doesn't have this problem because you're never going to actually execute runtime code. So, right, I went, right, stop everything we're doing. We need FFI. Let's figure this out. Otherwise, what's the point? And at this point, I realized that the implementation was so bad, I had to throw it away, because there's just no recovering from it. So once more from the top, restart everything. We've learned lessons now, and let's do the backends from scratch. And as you can see here from the stats, at one point it was like delete the old backends. There's thousands of lines of code that I had to throw away. And then since then, 23,000 lines of the interpreter, the tree walking one, and 22,000 lines of the bytecode VM. But then D hit me a second time probably because of my work with Python and Sil, I was used to having one type called a value that can hold anything. And in terms of thinking about things, it made things easier because then I could write an eval, and I had a REPL as well. So you have to return a value somehow. So all right, well, let's have a value thing that can represent any D type. And instead of using a variant, I decided to use a sum type because that was, cleaner. And all right, let's do this. And I can write tests like that. The tests look nice. I can go 3 plus 3 should equal value 6, et cetera, et cetera. But I then hit a hurdle with FFI because you need to transform this into actually binary things that you can pass to a C function, and then you get the result back, and then you have to box it back into value. And how did I find this out? Because it was taking days for the agent to cross the FFI boundary. I went, why is it taking so long? I went, well, I need to unpack this and unpack it again. I went, oh, that's going to be terrible for performance as well. And it did a lot of work before I noticed. By the time I noticed, it was bad. And then the interpreter did this. I had another agent writing the bytecode VM. I restarted bytecode VM again because I went, no, I don't want this. We want native layout for everything. Make FFI easy and simple, one, because it'll be less code, and two, it'll be more performant anyway. But, right, I already mentioned the value that every backend had to box into and out of. So this is the sum type I ended up writing. And then this is what happened with FFI. This is about 3,000 lines by the time I noticed to get a box value across the FFI boundary and back. And I went, no, this is clearly not what we want. And then AI oops. AI oops isn't AI is making a mistake. I am by directing the AI badly, or not directing it, as the case may be. So I went, right, let's restart the bytecode VM. We don't have any value from the get-go. Let's not make that mistake. But because there was already FFI marshalling code for the interpreter, AI used that as a hint that that's how the project worked. So it started building the bytecode VM back into marshalling, even though it didn't have to. And again, it took a while until I noticed AI decided to take dynamic arrays in D and use the length and pointer and reverse them. So then there was special code to put them in right order before doing FFI. And I went, why did you do that? I went, oh, sorry, I don't know. Well, just do the native thing to begin with. Why are we doing this? And this is what happens when you don't look at the code, by the way. So this is the code to swap everything, which you don't have to do if you just represent it the way the compiler does. And again, like, why would I have done that? Never. And then another oops. I asked the question, like, why is this so complicated? I went, well, you see, we have our own implementation of associative arrays. And I went, why? It's like, well, I don't know. This is what I decided to do. I went, no, just call the runtime. But I didn't think it through, and that's what it did. And again, it was a while before I noticed. And it did it twice. It did it for the interpreter, then it did it again for the bytecode VM with different implementations of associative arrays in D that don't even need to exist. And so I went, right, now the solution is you either interpret a bytecode compiled to D runtime instead, because it's right there. And it was 1,000 handwritten lines that I got to delete, including that struct there, which is native associative array. Again, it doesn't need to exist. And then again, I'll do the demo later. I seem to be going super fast here. So the conclusion, one of the conclusions, I bit off way more than I can chew. Like I went, do this whole backend because it's AI and it's magical and it can do everything. No, it will do it, but badly, and don't. The other conclusion is you need to learn enough to be able to make decisions about the project. I hadn't thought things through. I haven't even considered FFI or how D runtime would be handled or exceptions or any of those features. So I should have learned enough so I could have made better decisions and directed it better. You have to write down everything you know about coding and how things should work. You can't just go, it's in my head, so it will know. It won't. So the tiny little details about how you want the code to be laid out, et cetera, it has to be written down, and even then they won't do what you say anyway. I needed to understand the technical options deeply, like really understand the trade-offs and what's happening and the binary and the performance. And one thing that's really important in this age of AI is that your code base is a context in which the agents operate. So because there was marshalling code through the FFI, a next agent went, well, this is what I should do. So the worse your code base starts looking, then the worse it will look, and you end up in a feedback loop that's not good at all. And so it's even more important today that the code is squeaky clean and amazing, because it will be the example that further agents will use when writing new code. And software engineering matters even more than it used to, I think. And this feels familiar to me, because that's a screenshot of a game I wrote, and that was the third iteration of the game, because I wrote it, and I cowboy coded it, and it was my first big project. And I ended up writing myself into a corner, and I couldn't add new ships, for instance, because I'd hard-coded everything. And I went, right, throw everything away, start from scratch, redid the game. It was easy to add ships. But then it was hard to add different weapons, because I hard-coded that, threw everything away, start from scratch. And that was easy. And pretty much everything I learned about software engineering and what not to do was from writing this game 3 times. And that's what's happening in this project. I'm on the 3rd iteration of this because I keep screwing up. And I'm learning a lot about how to basically manage AI agents. We've had talks about that already. And I'm trying to, show the lessons I've learned here so you don't make my mistakes, but even though that's not how anything works. That's like having kids and trying to tell them, don't do this, trust me, I know, and they're just going to stick their finger in the socket anyway. So you're all going to stick your fingers in the socket, but you'll recognize maybe some of these things, and hopefully not all of it. And somehow I've raced past a bunch of slides, and we've gotten to the end here. So, thanks.
All right. Do we have any questions over here with
Walter does.
I think it's really cool that you've been investigating various ways of trying to make this stuff work. Although it didn't work out, I think
It's working.
It is working?
Yeah, I'm in the process of.
Okay. Well, I think it's really valuable that you tried all these different approaches to it. And anyhow, I think it's pretty cool. I like to see the end results.
Well, right now the end results are terrible. That's why I'm doing it from scratch. Basically what happened is I did get to the point that I could interpret serial unit tests, but compiled code did it in a second, and the interpreter took 2 minutes. That's not what you want.
I've taken a run at improving the CTFE interpreter, and Stefan has also made a run at it, and it's been very resistant to change, shall I put. So if you can replace that with a better, faster CTFE interpreter, I think that would be really...
I am 100% sure we can. The thing is, I'm so invested in this now, I just want to finish this first before I do anything else. It's like you with the code gen.
Yeah, I get wrapped up in the code gen and don't want to think about anything else.
Yeah, that's it. If I actually just wanted to better CTFE engine, I would have one right now, because it's not that hard, because it's way less things to do. There's no FFI, there's none of that.
All right. Well, for anyone else interested in doing things like that, one of the problems that DMD has is a very poorly done function inliner. It's overly complicated and overly restrictive in what it can inline. So if somebody wants to try out and follow in Attila's footsteps and come up with a better function inliner, I think that would be quite a nice contribution to the front end.
As I was saying yesterday, we have AI. We can do anything. We can fix everything.
Comment and a question. Generally speaking, the way that you sidestep stuff like the array order or the associative arrays is the first thing you ask the AI is think about this, then make an extremely detailed code level plan. Did you try that, or?
No, because I was lazy. Basically what happened is I was lazy and uncurious, and that's one of the things I learned from this is you can't just switch your brain off and say, make me a D backend, make no mistakes. It's, hang on, let's think about this thoroughly. What does that entail? And talk to me, teach me the things I don't know yet, and then you can make decisions. So one of the lessons I learned is you have to think even more, not less. You can't just go and discover along the way, because by then it's too late and you have to restart from scratch.
I mean, you can. It depends on your budget. In that vein, how much do you spend on this?
I don't know. I'm paying $100 a month to each Anthropic and OpenAI, and I run out of credit like every week. But basically, if you look at the sessions, I think at one point it was like cost of that session alone was 200, and I pay 100 a month, so a lot.
So does this mean that you can't really give a problem to AI and expect it to generate? You have to come up with the top-level design and then ask it to implement a top-level design. So there's still a role for the software engineer.
No, absolutely. And it's more than that. You need to understand the problem really deeply technically. It's basically, I think Mozart was playing piano when he was 3. It's a bunch of Mozarts. They can play piano really well, but they're idiots. And you have to check on them constantly because, I don't have kids, but I'm told that the scariest sound for a parent is silence. It's like, what is happening? And it's basically like that. You have to keep checking on them. It's like, what are you doing? And it's nearly always a dumb thing. Like what happened to me yesterday was I went to review this pull request, and it's like, what's this pull request doing? We're comparing dynamic arrays. I went, okay, why did you write 200 lines? Well, because. I went, no, that doesn't make any sense. That can't be right. And then after back and forth, they went, oh, maybe we should just, bicompile the DMD's lowering. Why aren't you doing that already? That's obviously the right thing to do. So, and another lesson is treat them as cattle, not pets. Just kill it. Like, if it's gone too far, just kill that session, kill that agent, pretend it never existed, kill the work tree, start a new one saying, we're going to do this task. Also, by the way, by no reason at all, don't do the stupid thing that, I don't know why I'm telling you this stupid thing. Don't do the stupid thing. Because, a previous one did. And it's constant vigilance, because you can't it's mistrust and verify. It's not trust but verify. It's mistrust constantly and verify.
Cool. Do we have any other questions? Yes.
Maybe more of a comment. I've mentored a student for the Google Summer of Code who did a performance regression publisher bot. And for the Symmetry Autumn of Code, he submitted a project to make the CTFE engine to refactor DMD to make it more pluggable, to fix all those things with AST mutation that makes it easier to plug in new backends. So just wanted to make everyone aware that if he gets selected, he can work on that, and maybe you can give him some tips or things you found. And
yeah, or mentor maybe, because yeah, absolutely, that makes sense. But it's a lot of work, and the thing is, the AI just makes me feel like I can do anything because you can, and all I need is time and tokens, and we can get anything fixed. But I mean, this is coming along. I'll do the demo at the Lightning Talk.
All right, do we have any other questions? Looks like a no to me. Well, thank you, Attila. All right, that one wrapped up a little bit early, so get back here for 10:30 for the next talk. All right, how we doing? I think we're all upstairs for a change. I'm kind of impressed. I mean, none of you are paying attention, but I am kind of impressed, Stephen. Just everybody look at Stephen. Everybody look at Stephen. Everybody look at him. Look at it. Oh, there he is. Hello, how you doing, mate? Guys, we have a first-time DConf speaker. Hey, so Noam, take it away for us, please.
Okay. Kind of a tough act to follow, but I'll give it my best. So, hi, my name is Noam. I'm a team leader at Weka. And I'm going to talk to you today about shift left that we're doing in Weka. And I'm going to talk about a particular instance of that shift left, what was difficult in practice in making that happen, and how we're dealing with it, and where we are in the process of dealing with it, because as you can see, it's going to be a very large project, and it's going to take us a very long time to complete it all the way. But basically, the headline is we have a very mature code base. I'm going to show you in a moment how mature it is. And we want to do a shift left. We want to move more towards unit testing and testing small components of the code individually and not the system as a whole. So a little bit about me and a little bit about the presentation. So like I said, I'm a team leader. The part of the code that I'm going to be focusing on is the RAID. We'll talk in a moment exactly what RAID means in the context of Weka. And I'm going to talk about why we want to make a change. We're not going to talk about the change itself. When it was explained to me, it was a 5.5 hours session. And we do want to break for lunch at some point, so we're going to skip that. But I'm going to need to give you some background to understand why this is difficult for us. As part of that whole change, I'm also going to have published an open source in D that I think will help us and maybe help all of you if you're also going to go and do similar things and use unit tests in your code. Okay, so this is not about what we should have done, but it's what we are going to do to deal with the problems that we've created for ourselves. So what are we talking about? The code base started in 2014, so over a decade ago. It's way over 1 million lines of code, lots of files. Weka is a very big system that supports very large clusters, up to hexabyte of data, tens of terabytes of read and writes a second. And it's a massive, massive system by this point. It started, as usual, something a bit small, but over time, it grew. And right now, it's very big and very complicated. This is an overview of the system, very schematically, just to show you which part of the system we're going to talk about. So what happens is there is a client, somebody who wants to do some sort of file system operations. That's the service that we provide. So they're using usually something like POSIX or S3 or NFS, some sort of protocol to do the actions. That goes to our front end that interprets the request, knows to distribute the request to the relevant backend. The backend needs to read or write the data from the disk. That's the RAID part. And the RAID part really distributes the read and write request across many, many different SSDs or hard disks of some sort. So a few points of interest. Everything you see in this slide from the front end to the RAID is pure D. All the system is written in D. And really, the RAID, as you can see, is a very fundamental part of the system. Like if this part malfunction, not something goes wrong in the system, everything goes wrong in the system. Like this is the very basic building block of the system. And the point of the RAID is really be able to read and write data to the disks, which is the very basic thing that any storage solution needs to do. So why is this complicated? Let's give you some sense of the complications. So we have something called a bucket. A bucket is really, in the worker terms, a logical processing unit. This is the thing that does all the decisions that have to do with a certain amount of the data. Which bucket handles which data depends on some hash function that we have. But we distribute all the operations across many logical computational units called buckets. Each bucket maintains certain amounts of storage, which is divided into placement, which is like, I think, it doesn't say it here, but 128 megabytes. And that is internally also divided into stripes and blocks of data. And the reason it's divided this way is so we can have redundancy. So if something goes wrong somewhere in the system, we can still do reads and writes properly. So let me give you an example. So let's say I have one placement and I have 5 + 2 stripes. That means that I have 5 data blocks and 2 parity blocks, which means that if one of my 7 servers goes down, there's still enough information, because the rest of the servers are backing it up, to make sure that I can still do the read and writes, still be consistent. OK, so far, so good. What's the problem? The problem is something that we call dirty. Because we are doing reads and writes across many, many machines, in order to make sure that if one of those machines goes down, we still have a functional system, things can go wrong on one of those machines. Something fails, there's a network error, the drive is busy, I don't know, whatever. We try to write something, it doesn't go well. So the mechanism that we have is that we go and say, OK, something here went wrong. We can't be 100% certain that everything is as it should be on this placement. So we raise a flag. It says something here isn't correct. And on the background, there's a process called a scrubber that goes and tries to fix those errors using the parities that we have in the system. That is a good solution insofar that it works. And it works well for over a decade. Like you have a system, and it ensures its correctness, even under faults. The problem is we had one fault of 4K read or write usually, and we made the whole placement be dirty. So you can see on the slide, it's not even to scale. It's allowed, we had a small problem of writing a small piece of information, but a much larger amount of data is now considered compromised because of it. So it's fine, but we took a small problem and made it bigger. And it costs us. So it costs us in many, many aspects. I wrote it down on the slide. I'm not going to subject you to me reading it. But the basic problem is this. Small maybe, temporary issue on the network suddenly becomes a permanent and large problem. And when you have a large enough cluster, those temporary conditions will start to accumulate. There are too many machines. And when they start to accumulate, you can also get into trouble, and you don't have to. Like, you've made things worse for yourself, in some sense. So the idea is basically we want to change the way the algorithm works, so we'll be able to localize the problems and fix them much more precisely and not amplify the problems that we encounter, which is not what I'm going to talk to you about today. So all of that preamble was to say what I'm not going to talk about. What I am going to talk about is the problem, since this is a very fundamental part of the system. The way it's usually tested today is part of overall system tests. So every feature that tests something about itself also implicitly uses the RAID and tests the RAID along the way, because it reads and writes something to the disk. So if we are to make changes, we first of all will make a lot of impact about the entire system. And it's very hard for us to be certain that whatever we're doing is actually working, because there's not a specific tests for what we are changing. So before we do the cleanup of the dirties, we need to make some changes to the testing environment that we are working on. Yeah, Sean Bin is here to help me to point out that you don't simply go and add unit tests to a few thousand lines of code and expect it to work perfectly well. Yeah, it's a bit more complicated than that. So there are constraints. The slide says we set for ourselves, but that's a nice way to say that we have no way of avoiding those constraints in most cases. But we like to pretend that it was a choice. It makes us feel nicer. The crucial part is that we can't have any performance impact on the RAID. This is the hot path of the entire system. Every small change that would be imperceptible performance-wise in any other scenario would be felt very dramatically in this case. We want to be able to do several levels of markings. So we'll talk about this a bit more in a moment, but the RAID interacts with a lot of the system, and you don't want to always use the entire system to test the RAID. You want to be able to separate the RAID and isolate it from the rest of the system. And there are several ways or several levels of isolation that you may want to have. We would like to make things run at compile time as much as possible. Saves time, mostly. We can't do any big refactors, and we can't freeze the code. So we need to make a lot of changes while the system keeps moving. And last but not least, there are a lot of limitations in the code, the way it's written today, that is not helpful to isolating and writing unit tests. That is true for our code and the code in general. So what does those restraints translate to? So most of the code in the RAID is, of course, not using garbage collector. And most of it is also marked no trace, which means that when the code runs, we don't have actually debugging information about which functions are called. We don't have visibility even for the running of the code so very well. We can't use any virtual calls. Everything needs to be related directly. And we can't add any memory to the code either, because every little thing that we add will have a negative impact on the system. And those are a lot of lines of code. Okay, well, we talked about, previously I talked about mocking. That's a good place to talk about it. So the main thing that the RAID is using is, of course, the SSDs themselves. That's the main thing that they call and make a request to. So we did some thinking about it. There are three things that you can conceivably want to use when you're doing testing on a component like the RAID. The first one is just use the real part of the system. This obviously has some advantages. You're testing the real thing as close as you can to what you're going to be shipping to the customer. So it's much more reliable and much closer to the actual product that you will ship. But it's also the most expensive one, because you will need actually a much bigger pile of code that handles the SSDs and maybe SSDs themselves, and it's bigger, and you need to link the whole thing, and it's heavy. It's just heavy. The second thing that you can have is you can go, okay, but what about virtual disks? I mean, I don't have to have an actual physical disk. I can just take a bunch of memory, says, okay, dear memory address space, you are now a disk. Please behave as a disk. When I write something to you, write it down. When I read from you, you can read from it. Excellent. Fine. Certain limitations. It will obviously be smaller than a real disk, because I can't make an entire disk in memory. But it's faster, it's smaller, it's in the same process, a lot quicker and a lot easier to do. So the unit test will run that much faster with a virtual disk than with an actual disk. It's still not good enough for many cases. Why? Because imagine that you reach a certain edge case or corner case in the flow. So if you want to test it, you actually need to do all the operation to get the disks to the position where you had the original problem. So you need a lot of setup to get to a certain position. If you have a problem, only when two disks are down and one of them is a member of the, and written the, and like, okay, it's a lot of setup to check the situation. Much easier would be if we can just mock it completely and just say, okay, when I call the SSD, this is the response I want to get. Like, I want to read like a certain value. I don't want to actually write it in advance. Just when I read it, give me that answer, or give me that failure. I don't want to get the disk to the default position. I just want to imagine that it has a fault position. The advantage, I'm much more focused on what I'm actually testing. The setup is much quicker. It is more work, because you need to specify exactly what the response from the virtual disk would have been had it been there. So you need to be very specific about what you're doing. You need to say what the disk will reply in every case, and it doesn't just happen because you said read from memory or something. So very useful for complicated scenarios where you don't want a huge setup, but maybe an overkill for a simple test. Okay. Okay, so like I said, we would like to run the tests inside the compiler. The reason is that tests that are inside the compiler are run in seconds. I know Attila just said that seconds is way, way, way too long, but that's the reality. It takes seconds. But running, building an actual executable and running it is minutes. It's not seconds. I don't know how Attila feels about that, but probably not so good. But the way we're doing it today, which is like, let's provision an entire cluster, that's half an hour just to set up the system. It's you need several machines. You need to install everything on those machines. You need to connect them. It's time consuming. The thing is, both 2 and 3 actually have the same solution, fortunately for us. It's all about dependency management. If you can disconnect the dependencies, you don't need the entire system. You can use mocking. And if you don't need the entire system, you can scale it down to hopefully compile time, if you can make it. OK. So almost last constraints. We can't do any bigger factors. We can't freeze the code. This is a live project. This is a live product. Customers are expecting, fixes, new features. We can't say, OK, everybody, nobody pushes anything for this repository for a week. We need to get things done. And frankly, even if we could, a week wouldn't do it. It's a much bigger project than that. So we need to somehow manage to do all of this while the train is moving. OK. And like I said, we've encountered some parts of the code that people have written that works well, but not really helpful for us as the people who need to now test it. I'm not going to go over all of it, but you can see the word shared appears many times on those errors. Shared information is very, very difficult when you get to, just want to test something because it's global in a sense. Yeah. So, like I spoiled myself a little bit, and I already told you that the key factor here to realize is that this is a dependency management element first and foremost. If you could have solved that easily, the rest would go much smoother. So it's really a three-step solution. One is identify the minimal points where we have interaction that we can break the dependency. Unfortunately, the code is not, designed by contract or a very clean interface. It grows organically, so this is not a trivial task to identify where we can break the code. Inject some sort of dependency management mechanism at those points. And we're going to use version unit tests to make sure that those injections only appear on the testing environment and not on the production environment. So we are certain that we are not degrading anything on the product itself. And then once we have the dependency injected, we can connect it to the unit test as a whole. OK, so first of all, you need to identify all the dependencies that the rate component has. And this is a partial list of things. But the crucial one, like I said, is in the top is the SSD, because that's the thing that the RAID actually invokes. Everything else, the callbacks are easy. You can just give the unit test the callbacks that you want, not the callback you would have gotten in the actual system. That will work fine. Time and events and all of those things are, those are problems, but those are problems outside of this particular project. Those are general problems, and there are other projects in the company that are working to help with those as well. The big problem for us is the SSD agents. OK, so how this looks like in practice. So in practice, you need to identify a location where we make the call, and using version unit test, you replace that call. So in production code, it stays exactly the same. But in the unit test environment, it suddenly becomes redirected to your dependency management mechanism. And that dependency management mechanism, as we can see, has a couple of options. You can do the real, the virtual, or the mock, as we've discussed before. OK, and the crucial thing is this is a very minimal change that you can do in the code. It doesn't interfere with anything else. It doesn't interfere with anybody else. And you separate your effort of unit tests from the rest of the development at that point. Okay. So, like I said, the dispatch dependency management mechanism really has an enum, which states which mocking do we want to use for a given test. Do we want to use a real disk right now, or do we want to use a mock? And this can be changed for every test, or we can run the same tests with different versions of mocks, depending on what we want to achieve. And the nice thing is, because we have reflection capabilities and templating capabilities, the call itself becomes the key that we use to redirect the call. Okay? Okay, so this is an example. So we have a small code of test, and what happens behind the scenes is that the RAID calls pull block. Pull blocks goes, it's a real function, it's not a test function. It goes and asks the SSD to do something. The SSD interface picks up that call, looks at the exact setup for this test, and decide whether to redirect this to a real drive, virtual drive, or just the pure mocking system. And then returns the call internally, and it goes from there, and we can see and we can assert in the end that we did get the expected answer, 0 in this case. Okay, so lesson learned so far from this effort. Most of this is things that if you spend any time in the unit testing environment, you will also hear. It's true for everybody else, and it's true for us. Teardown is an issue that people don't always think about in advance, but it's crucial. If you don't do the teardown, your tests will start to influence one another in ways that you don't expect. So you need to make sure that you clean after yourself. Globals are difficult. I know that's shocking statement. Build systems disagree. Like we are now in the process of moving to Basel from our old build system, and there are differences. You would think it doesn't matter. It's the code. Why should we care? But we care. It is what it is. Mocks drift. Like you write a code that mocks what the actual SSD code will do, but then the SSD people enhanced it, changed it a little bit. Now you need to make the change yourself. Reflection helps because the code sort of adjusts itself automatically, but you have to not just change the signatures and the input parameters, you also need to make sure that you change the semantics properly. And that's not something that reflection can magically do on itself. Flaky means wrong. If system tests can sometimes be flaky, you know, there are a lot of components in system tests that you don't actually control, and something can be weird. Unit tests should not suffer from that. They should be very, very stable. Either they work or they don't work. If they are sometimes working, you probably did something wrong, and you should go and check this out. And lastly, keep the production files as clean as possible from the testing code, separate them. It will help you make sense of what's going on. Okay, that was very nice, but where we are actually in the timeline of this project, we've made some progress. I was hoping to be, when I first submitted this talk, I was hoping to be standing here and tell you more about the great success that we had, but life got in the way. And we are not as far advanced as I would have liked us to be, but we're making progress, and this will take time, but we are making progress, and by the nature of these things, at some point we will complete this transition. Okay, I am getting near the end of my time, so I do want to say one other thing. As we grow the number of unit tests that we have, there are some things that become more and more apparent, and that is that you need to pay more attention to how you manage your unit tests. When we have a small amount of them, it's one thing. When you have a large amount, it's different. I had the previous experience working with an infrastructure called Google Test. I don't know, please raise your hand if somebody had some experience of it. Okay, not a lot of people, but some people did. And Google Test, for me as a user, was very nice in the sense that it gave structure. It allowed me to batch unit tests by topic and manage the tests nicely. And unlike the test that we have today, where we assert on an error and then it stops the entire run of the execution, the asserts in Google tests allow me to assert and stop just that particular test and then allow the other tests to continue running. So I don't need to see all the problems one at a time. I can see them all at once, all the tests at once. So I thought it would be nice to have something like that for D.
We
do? We do?
Yeah.
What do we have?
Multiple test runners.
Sorry?
Multiple test runners.
Multiple test runners. Okay, I came with a different solution. And I asked Claude to help me write D-test, just the same thing as Google Test, but with D. Just the Google testing itself, not the Google mock, for those who know what I'm talking about. And it's very nice. The thing is, Google Test is a little complicated because they need to use macros for various things, but I don't need to use macros in these because it's reflection mostly. It's much cleaner in that regard. You can see here that it's a mixing template instead of a huge macro that it would have been had this been written in the C++. And yeah, it's basically now open source since yesterday. So everybody who can use it. Claude did a very nice job of turning the code over. Some parts it failed. Those parts I did not include in the repository. Just told them to drop this, which is fine. It's not it's the part of the Google test that I don't actually like. So good for me. And yeah, that's an example of what it looks like. You can see it says we have 12 tests in one suite, so one area that we want to test. There are 12 cases. One succeeded, one failed, and so on and so forth. And it tells you what the failure was in a reasonably verbose way. Yeah, and the fact that you have setup and teardown means that it helps you manage those dependencies that you clean after yourself, and one test should not interfere with another. It reduces the chances of that, let's say. Okay. So, final lessons. If you want to do something similar, it's a dependency problem, first and foremost. You need to realize that and treat it properly. Let D use do the injection for you. We did version unit test, but you can also use static if. Start with keeping the default as what you have today, and then change it later. Separates the concerns. Compile time as much as you can. Use fixtures. They let you manage your tests independently. And that's it. Thank you very much. Do we have any questions?
In a previous slide, turn on. There you go. In a previous slide, you were saying that you have to review the mocks against production because they drifted, but that doesn't scale. You need to guarantee it somehow in code. So the way I've done it was contract tests. So you verify that the mock actually does what production does separately, and then you use the mock.
So yeah, so that's a good question. The answer is it depends on where in the lifetime of the development you are. Once the unit test falls in, it's part of the build system completely. And then if somebody changes anything, say on the SSD side, and changes the things, it will break for them as well. So they will know immediately that that happens.
Right.
But until that point of time, since this is background task that takes time and just the way that it is, the code sometimes sparks for too long, let's say, until it merges in, because we're busy doing something else, and in the meantime, the SSD people are making changes, and so this is a matter of conflict between things entering into the main branch, mostly.
All right, and then I was wondering why you wrote D-test. You were saying, I wish we had this in D, but the 4th and 7th most popular Dove packages are test runners.
Okay, so first of all, I wasn't aware of that. So that's one part of the answer. The second part of the answer is that I really had a good experience with Google Test, and I know how to do this, and I know how to work with it, and I know all the niches and purposes. So
yeah, even the output is the same.
Okay.
No, even the output that you wrote is the same as Google Test. That's what I'm saying. So I can see that you're used to it.
Yeah, it's deliberately the same in that regard.
Yeah, I can tell.
Yeah.
Thanks.
All right, we have a question from Ricky on the internet here.
Okay.
Have you considered part of the problem you're facing with differentiation between die now and keep going is that you're using assert? With assert error, something must die. You should use exception.
We can use exceptions. It is, in fact, what happens behind the scene when we're using Google tests. But even with exceptions, you need a mechanism around it. You need something that will catch the exception, because if nothing catches the exception, you end up with exactly the same situation that you throw an exception and all the process falls down. So you still need a mechanism around the exception, and this is part of what the code does, actually.
I just want to make sure you're aware of this. You can write a normal unit test block and still wrap around it. Like maybe talk to Claude about that. Even if you have a normal unit test block, you can put annotations in it, and you can fish out these annotations in your test runner, and then wrap a try except or even catch asset error if you want that around the entire unit test block in the runner. That is something that is technically possible, though it's a bit arcane.
Okay, thank you.
All right, do we have any other questions?
So I always found these unit test blocks to be not very powerful. So I understand you want your own flexible mix-in thing, but you're also kind of clumsily, using strings for codes. I wonder if you considered filing an enhancement request for these unit tests feature that makes your unit test more native and supports your real-world use cases.
So no, and for a particular reason. Obviously, it also comes down to personal philosophy, but I don't think that this kind of thing should be inherent into the language, because it should be something that is easily switchable if somebody wants something else. So I don't think this is a language level feature. There are libraries and open sources in every system, and it's for a very good reason. So I think this is exactly the sort of thing that should be like an add-on that you can decide if you want or don't want.
Like the language should facilitate those add-ons. Like you shouldn't have to write different syntax.
Let me handle that one. Don't bother filing the request because I'm going to do that anyway. This is on my to-do list, so.
Okay.
Okay.
All right. One more good question. Let's have one more good question to wrap things up. It is a good one, right? Anyone? No? All right, and then let's just wrap it up. Thank you.
All right. Thank you.
All right, the last talk before lunch will be at 11:30, and I believe it's another first-time DConf presenter, so back for that. That I don't think should work. Yeah, no, if you actually want to click it, we can get one for you, but it is a full fat USB, so that. Yeah, I'll give everybody 20 more seconds and then I'll kick it off. Yeah, that's good. Let's go. Okay, everybody, welcome back. Oh, one woo, that's what we want, except a lot more than just one. More woo. That's better. Yeah, it turns out my memory is in fact terrible, and this is not a first-time DConf presenter. So, give him a minute. This is what I want to see more, people texting on stage.
I'm texting.
That's fine, your talk hasn't started yet, so you can do whatever. You can like skip and jump or whatever. Whatever. So what do we got? Yes, we have 5 lightning talks today, so that's good. I don't need to harass you people for more lightning talks, but tomorrow's a different story. I still need to harass you for lightning talks there. So please think of ideas and then let me know. Otherwise, Emmanuel, let's give it up for him.
All right. Okay, thank you very much for being here for this talk. Today we are talking about import C. How many of you guys are happy to see import C being improved? That's amazing. So I did import C work this past Symmetry Autumn of Code with Dennis Koppel, and I think it went so well. We had so many fixes. There were so many things that were broken, but the good news is that we got them fixed. And so a little bit about me, I'm more into systems, like anything systems, so compilers, operating systems, like the networking, storage systems, device drivers, and I also do code security research as well, very interested in that. So the purpose of this talk, I'm sure there are people here who haven't really tried using import C before. And so I'll be talking a little bit about like simple use case, how to just set up a simple C code, compile with DMD, and then maybe get a C code, import from a D source file, compile, and get things running. And then also share the recent improvements that we've had with import C. So the basic idea of import C is that you have a compiler, a D compiler that has a C, I call it a virtual C compiler in a D compiler. So it can take a C source file and then parse it and then make meaning out of it in semantic analysis and then take it to your backend, make it work. Like just take a normal C program and make it work. So we know that a normal C compiler, we know C programs have headers, and then they also have like normal C source files. So you can include your headers in your C file. It does a copy and paste, and then preprocessor stage, and then the sources all go to the compiler, and then produces assembly, and then your assembler gets into whatever, if you are linking, exactly. So with your C file. And then similarly with a D file, D doesn't have like headers, basically. So it's mostly D, so your D compiler to like DMD or LDC, either taking imports to import other models from a model, or maybe just compiling a single source file directly. So you have like one single D file and then let's say DMD. All right.
The DMD compiler doesn't generate assembly. It generates object code files. I'm not sure if LDC or DDC generate assembly.
Okay.
Oh, if anybody didn't hear me, The DMD backend does not generate assembler. It generates binary code directly.
Okay, by default, because I've no assembly
Always.
at all. Okay.
Yeah.
Then thanks for the correction.
Okay. It compiles much faster if it doesn't route
Okay.
things through an assembler.
So straight to bytecode directly. Okay. Thanks for the correction. So, so now with import C, you can either have a single C file, and then you have your Lexa, and then your C parser, and then it passes the C code that it sees, gives meaning to it, and then creates DAST. But then it also makes room for certain things that C has that D doesn't have. But in the end, it's basically D AST nodes that are being, but there are some C AST nodes too. So the ones that we can reuse in D for C, we just reuse them. The ones that we need maybe new additions, we just reuse a new AST. And then when you are importing a C file from a D file, then the imported C file is acted on, and then you have its own symbol table, and then now the symbol table gets included with the current D symbol table, so then you can get to call functions from your C file that you've included becomes into a single symbol table. So that's basically how import C works. So either you can basically run single command on a C file or import a C file into, but then you can also do it with headers. Like if you have headers in a C file, DMD has its own way, not DMD, the D compiler has its own way to resolve that and make that one also work. So that's basically a simple mechanism with import C. So as I said, so it has a dual, I call it a dual use case. Either you import a C source from a D source and compile, or you compile a C source directly. So it's a simple example of using import C. You have a simple C file here, and then just contains a C func and returns. And then you have your D file here, and then it has your main, and then calls the C func from the imported C file. So when you are compiling, you make sure you pass both sources on to the compiler, because it's problematic if you leave the C file out, because of it needs to resolve symbols. So you have to compile, and then so this compiles the C file, gets symbols for the D files, and then every call from the D file gets to call the functions from the C file. So this will produce a simple output for you, basically returning nothing. So call the C function. So it will create an executable D file, and then you call it in your path, and then you can just run it. And as this function is actually producing nothing, so there's nothing to issue. But then when you're compiling your C sources directly, you can also have a simple C file.c, just define a C function, and then int main, call it, return 0, like normal C file syntax, and then you just run your DMD compiler or your LDC compiler on the C source, and then you get your executable, but then you have to make sure you get the right executable sometimes. But DMD will produce the same executable as the source file most of the time. So you will see it in your directory, and then just load it into memory, and then everything's going to run. So now the other truth about C. So is import C a considerable replacement for C? I don't think so, because I believe that C is not going anywhere soon in time. Like our operating systems, drivers, if you go to the electronics, everybody's still using C. And I'm not sure people are willing to do the rewrite, the entire rewrite. But then we know that right now Rust is getting like few parts into the Linux kernel and some bin utils and all those things. And then I think FreeBSD is also experimenting with Rust. They have, I'm not sure they have added sources to their kernel yet, but I know they are experimenting to see if they can get Rust into the kernel. But then that would take like very small part of the kernel, because like C is still there. C will take majority of like 90% or 99%. Yeah, and then 0.1 for those that I'm not aware of. Maybe some other operating systems are considering doing some work with other languages into their kernel. So D having an ability to compile C source is a very good adoption mechanism for D. At least we know that D can do secure stuff on your code as compared to like C++, as compared to C, sorry. Yep, D with buffer overflows and all these things, like D is going to make sure that things are checked properly as compared to C. Exactly. So what I personally use import C for, so for now I use import C for simple code security checks. So we know of supply chain attacks that these attackers use like Unicode into some source files. Maybe example, if you are doing a copy and paste, maybe over the network or something, sometimes you can get Unicode embedded into them, which you may not see. So this is a report from 2026 about so many visible code, even on GitHub. GitHub were seen to be doing some code scanning on sources that are being pushed, but still, these attackers find a way to use like invincible Unicodes and then to do malicious stuff, to get Trojans to them and so many things. Yep, so I happen to manage small servers that run so many services like web, mail, storage stuff for people, and then if sometimes there's a need for some C source files that people use over the network, I happen to maybe run DMD on them. Because if there's a Unicode attached to your C source file and then you run it through a GCC compiler, it's going to warn you that maybe this Unicode, but then it's not going to stop you from compiling. But then if someone who is not really aware of what's happening, and maybe it's something malicious, GCC will not really stop you, but DMD will tell you, hey, you cannot compile it. Like, it's an error. It's because D has no. So I have a simple example here with a simple code that I usually play with, and then I just copy it over the internet to a different source file, and then I intentionally leave a small space before the C increment, the C variable increment, and all the time it adds a small Unicode to it, and so if you are compiling your code, this is what DMD tells you. This is just a C source written and then copied over the internet to a different C source file. But then when you are trying to compile, DMD will not allow you to compile because it tells you that the character 0xa0 is not a valid token. And this is something very common that we know, that this is a Unicode for the breakline, no breakline spaces. Like if you are, so these are part of the things that I'm personally looking to use D for, like security research in sources. So this is things that I play with once in a while with import C, and I have some small C codes that I run import C on almost all the time to just use that executor but not use GCC. Yep. And so now the whole idea of import C is that we want to compile C sources, but we know that there are things that C supports that D is a no-go area, and there are things that D supports that C is also a no-go area. So we have to balance it to make sure that we accommodate each other. Like, you are the bad guy, I become bad for you. I am the good guy, you become good for me, so that we can work together, exactly. So these are the recent improvements that we did: designated initializers, compound literals, functions and variable declarations, macros, and then we did some built-in implementations, and then DMD, backend symbol duplication, static linking, complex numbers, so many things. So I would want us to go through most of the fixes that we did in both DMD and in the D compiler, not just DMD, but Yep. So this was the first fix that I encountered. This was the first issue I actually encountered on the DMD compiler. I was just playing with it, but that wasn't my first issue to solve. But I always like to talk about this because this gave me a very good experience in DMD especially, because when you have this, we know this is fine with GCC. If you have this C source file and you run it to GCC, you can create an object file from this and link it with any executable. But then DMD was having a very funny problem because when I compiled it, I wanted to look at a symbol table of what was being produced. And this is what I was getting for this source. When I used DMD to produce an object file on it, I was having this symbol table. And we know that we cannot use this in linking because it's going to carry that symbol duplication. And so I tried it with LDC, and LDC worked fine. LDC produced just one symbol for me and not duplicated symbol. So because they worked on LDC, I knew that, okay, there was a backend problem. So I should go to the backend. So I didn't even look at the front end. I just went straight to the backend. And I would just change one variable, and everything is broken in DMD's backend. Now, just change one thing, and everything is broken. I remember, so I traced it to find where the symbols were being resolved in DMD's backend. And okay, this is where the C symbols are. So I should just check if this symbol has already been resolved, then do not resolve the symbol. That was the only thing, and it was running there. You have things broken on Windows, few things broken on Linux, x86, and it's working on x64, and everything was broken. And after a week, I was like, nah, this is not a good place to stay because my mental health was at stake. In DMD's backend, I was like, I'm not going here again. This is my last. I have nothing to do with the backend. So I left it, and then I came to work on other things, and I was like, I wrote it down that I have to find where it is in the backend to fix it. But then I think once in a while, it could just come into my mind that I'm sure it's something I'm doing wrong in the backend. But then you just add, sometimes I could just add a simple for loop doing nothing. Just a simple for loop doing nothing, and then things are broken in DMD's backend. Just a simple for loop. Doing nothing, things are broken in DMD's backend, and then I could send to my mentor, and then we will all be confused, what's actually going on. So I just left it. But at some time, I realized that, okay, I could go to the front end and see what I could do about this issue and find a very simple semantic of fixing it. But then I realized that Walter had left a comment in DMD's backend that he did not resolve static functions. And so it came to my mind that, okay, I could take advantage of this and go to the front end. So what I was doing was, this is what now I do to all the symbols that are being declared more than once in C source files. So you have int A globally. I just mark two of them as static. So that was a simple fix, and that did the work and saved me from DMD's backend. I was like, thank God. Yeah, it saved me so much because I was like, okay, just make them static, and then just leave one. And then that worked so well. And then, so now we don't have symbol duplications in DMD backend on import C. And then, so now, if you compile your C source file, because right now, because of headers, you can have C source files having so many duplications because of the copy and paste during pre-processing. So you can have many C source files having so many duplications. So this is what did the magic for me, and I'm always happy about it that it was fixed in the front end. So the next one is designated initializers, and we had so if you have a struct, if a C source file has a struct like this, struct foo, and then two members, X and Y, and then you have another struct bar, and then bar has a member of another struct, and then you want to initialize your bar object, and then by designating all the members of the member struct like this. It was erring because it didn't allow more than one designator. That was like an intended error message that was left in DMD's front end. So this is what I was able to fix. It was just a simple for loop to expand the number of designators and just rerun semantic analysis on them. And so that was a simple one, and it worked so well. And then taking address of compound literals was also not working. So if you have a pointer that points to a literal, by reasoning, 8880 does not have a location in memory. So you definitely cannot give it an address. You definitely cannot access it by address, sorry. And so with what the C standard did is what I just looked up and re-implemented. It created a temporary variable that lives as the pointer lives. If the pointer dies, it's no longer living. And then we just reference it, and then we can use it. So now, this wasn't working. So if you have something like this in a C source file, you can easily compile it because like it has a temporary storage in memory, and then your pointer that you're trying to access to it can actually point to it and dereference it for data. Now, this one works, creates a temporary value and stores it later initializer. And the pointer points to it and uses in the lifetime of the pointer. So this is one nice thing that we're able to do as well. And so now, if you have these, you can try them and compile them in any of your C source files, and they work nicely. They work nicely. And then also variable redeclarations, if you have maybe an extend int and then an extend int, we know that these are allowed in C. But if you have different, let's skip this. So we know that if you have an extend int x and then an extend int x, the same external declaration, this breaks these semantics because like D does not allow this. And so we have to find a way to make it work in C, as in make it work on C source files, and still maintain it being not allowed in a D source file. Yep, and so this was a very simple one. We just had to check in the symbol declaration module and then checked if it's a C source file, don't make noise. Maybe just use one of the symbols and maybe end semantics for one, but then don't make noise, and then it compiles very nicely. And then same for function redeclarations in the local scope. So if you have a function like this void test, external int f, and then int f, this breaks these semantics. But then C is okay with this. So if f is already defined, so this also going through the same rechecking, going through the symbol redeclaration function, and then just making sure, okay, this is already defined. Don't make noise for this. If it's a C source file, just don't make noise for it. Be quiet, and then end semantics for one of them. Or maybe just replace one of them. Yep. So now these are things from powers. It's free from the bondage of these semantics. And then so these are things that you can have in a C source file and then run DMD on it and it compiles. So with macros, so this was one of the things that I didn't really have a good time with macros, but then, so we are playing with if namespace. This is a very popular macros that we know in Unix for getting the string length of network interfaces, right? So so macros can have different forms. You can sometimes see sources just have a macro defined for no reason, and then do nothing, just they define it. Sometimes you can have a macro being defined to a value, to an integer value. You can have a macro being defined to maybe an expression. You can have it defined to a string, to a function, or even to a braced enclosed expression. And then we know the if defined conditional compilation, and then if not defined, and then if defined, and then an end if, and then, yep, and then you can have a defined macro to a normal identifier. So these are the various types of macro definitions, macro declarations that you can get in C. So you have to accommodate the parser in D to make it work. We just have to make it work some way, somehow. Yep. So if you have define if namespace, so if D sees this in your source file, D will expand it to nothing. So it will just end it there, like don't do anything to it because we don't really need it. Yep. But then if you have a defined macro declaration to, let's say, 5, D uses manifest constants and to just create a variable and then initialize it to 5. And then so the variable will be available in the current scope, and so you can reference it anywhere in your code. And then if you have an expression like this, so this was just using template functions. This is to just return. So if you have like define if name size 5 plus 7, it has an auto if name size. So these are things that sometimes if they are not literals, they give a certain kind of, if you have defined with a string type like this, okay, D uses a num if name type because string. So let's say string 7 for like the manifest constants. Exactly. And then if you have an expression like this, enclosed in braces, D is going to do this, a template function with an auto return type, and then just return the expression to the template function. And then they work really well. These are things which we're already working in D. But then this is one of the biggest problems that we discovered. You know, in C, you can have a macro that references an identifier that has no meaning, and it compiles. You can have a macro that references maybe boy, but boy is not used anywhere in code. And boy is not referenced, and boy is not defined. But then C will compile it. But even though it's not being used, it's quiet. But then when D sees it, D always wants to be like, hey, I'm the straight guy. What is the definition for this? Because if you try to make meaning out of it, D wants to know where this is coming from. So this was one of the biggest. But when I saw this, I was like, okay, we can use an alias because like this will just reference this. But then if you think about using an alias, one of the painful things is that we know sometimes if you have something like this is very valid in C. You can have like even in C, you can have a macro that even references itself. Very common in C code. Maybe sometimes I just don't know why some codes are there, but like if name says, and then if you try to use aliases, you are going to easily break these semantics because like you cannot assign an alias in D. And so, and then as I said, if you have like a macro to an unknown symbol, C will compile it quietly. But then D will be like, hey, I'm the search guy. I need to know where you're from. So D will not compile it. So it's making noise. But then this was quite not stressful to work this around because you can just be like, okay, in symbol semantics, if I check an alias and then it's in a C source file, and then the symbol, I don't know where the symbol is from, just don't make noise, just be quiet, don't cry. And then, and also if an alias is self-referencing itself, and then it's in a C source file, but there was an attribute about like if the variable is a macro. So that also helped because when the parser is making meaning out of the macros, it adds an attribute and its macro attribute to it. And so it was able to maybe identify aliases that are macros and the ones that are not actually like macros, like real aliases, so that it doesn't conflict. So that was a nice attribute that was easily used in symbol semantics. So if you have this like a function, because you can have a macro that points to a function call, like a function that returns to the macro. But the painful thing is, if you want to create a variable from this macro, because most of the macros are defined not in function scope, sometimes, most of the time, you get them in global scope. And when D sees this, D tries to give like a global linkage, right? But then you cannot know the type, the return type of this variable. And then sometimes the compiler cries that the function you are initializing to the variable has no body, because like sometimes the function is not even defined in that same source file in C. And so if you have something like this, what will just come to your mind is, okay, just create a variable and initialize it with get if name size, and then create a call AST for it. But then it was always problematic because the var variable needs a return type, and then the get name size function's body must be known. And then DMD compiler was always crying that, and I didn't understand because I could have a simple source file and then maybe define the function and then call the function to a macro and then compile it. It will work, but when you try to apply that same code on a library, and then DMD will start making noise that this function is unknown, this function is unknown, this function is unknown. So what I discovered was that how D compiles like as let's say a collection of C sources, like if you have like A.C, B.C, C.C, and then maybe see if this C has headers included with macros. Let's say define if namespace to this function, right? Sometimes the function may be defined in another module, but then because of the copy and paste module of the C headers, maybe a header will find itself in a file that will have a macro included that will not be actually needed in that file. That's very common. You can find that maybe you want to use one particular function from this header, but this header contains different declarations, contains different definitions, but then you include them, and then the file becomes, okay, so many things. But then when this ceases, D tries to resolve the macros. When D ceases, and then D was taking the context from the current compilation unit. So if like when D is compiling E.C, and then you have the function defined in D.C, but this header has a macro definition pointing to a function that has been included in A.C, and then that function gets that macro declaration gets seen in A.C, and then D tries to resolve the definition of that function, but then it's not able to find it because the function is defined somewhere else. And then D can't wait because it's a variable initialized, and so D will need to get the function body of it. And so in the end, that was what I discovered, and then realized that using aliases was not the right solution for it. So as I said, so C always includes always leads to a lot of defines and declarations source after preprocessing. And then a macro declaration may have found its way into a C source file via includes, which may not necessarily need to be there. But when D tries to resolve it, it does it in the symbol scope of the current compilation unit, which does not find the definition for the aliased symbol. So this is what the solution that was come up, that was, because I actually hadn't, because this was what was done for in the previous codes that I came to meet, and I think I should have done this similarly for it, because now if you have like a templated function with an auto return type, because now we don't know the return type of the function. We don't know if the function is going to, you cannot define the variable, the type of the variable that you are creating. If you want to even create a variable for a function initialization, you cannot actually know the type, because then you don't really know what it's going to return. So what was happening was that an auto templated function that just returns it could easily pass compilation and then could be resolved at the right time when needed. So that was what was being used. So that was what we just adopted for the macro that points to identifiers, either known or unknown. But then we had already made provisions for C macros that point to identifiers that has no meaning in context, or macros that points to itself. So that was the easiest way that, okay, so we just check them, and then we show that if a C macro is this, it has no meaning, and then it's from a C macro. Just ignore it. Don't make noise, but end semantics there. So that was what also helped us. And then, so now you just know that when you are using import C on your C source files, just know that DMD frontend is creating template functions for identifier macros, your function calls, your direct identifiers, and your base identifiers. It was via an add non-array template function that was implemented. It was something I came to meet in DMD, which was making it work very nicely. And so that was the base name. And then we have the ondef if name says, so if you have ondef, it just checks up this current symbol table in that scope and sees if this macro, which has been resolved in either an enum or whatever has been resolved in, you just remove it from the symbol table in that scope, and then that works. And so just transitioning C's model to agree with D. And then for declaration with static libraries, I think it was one of the problems that I had seen on the forum that it has been there for some quiet now, because if you do a forward declaration and have the definition somewhere below it, if you don't pass the dash lib to get like a static library to have all your symbols resolved, initially it was making an error with the dash lib because it wasn't finding the definition of the top static function. So I think that was a dig that also, I thought it was a backend problem because the error was from the backend. But with what I had experienced in the backend, I said, no, I'm not going to the backend. So I had to figure it out in the front end. So, and I was able to figure it out in the front end because the front end was trying to replace the definition for a function that has been declared but has not been defined. But then the update function was not doing it properly. So it was mixing up with the symbols, and then I was able to find it that, okay, this is where it's supposed to be updated, and this is what supposed to, we need to find the definition. And then, so what I was doing was that, because it was a complex code that I didn't really want to touch, so the best solution we came up with was to just move the definition of the function, just move it into the addresses of the declared function. And then so that the compiler will see the definition on top of it, because it was always thinking that it has no function body. But then it was defined on top, so now we move the definition on top, and then we are fine. And then that works. So now you can build static libraries with import C in D. So with complex numbers, this was one also big problem in import C, that our complex numbers were not working. You were not able to compile C sources that contains complex numbers. And then the main issue was the decision that I saw in code that the compiler was trying to duplicate like the fundamental complex type and trying to use a new library struct complex. So D was heading towards a direction to duplicate the fundamental complex type, as far as I know, according to my knowledge. But then, if you care about import C, we needed to revert from it and then go back to, yeah?
Yeah, I was going to rip out the complex type out of D and out of the code, but I realized with import C that using the complex library type was no good, and so having complex numbers in the front end, in the D front end, is here to stay.
Yeah.
And you're quite right.
And thanks very much for leaving, because I saw a comment that I think was about to be deleted, but then for some reasons it wasn't. So
well, it was deprecated for a long time, and we were going to remove it, and I'm glad we didn't remove it because it turns out to be critical for import C.
Yeah. So I was doing so many compilations on the S7 library, and then S7 library, I'm sure many of you have seen it. It's a very scientific library, heavily involved with complex types. But then when you are using complex doubles, that was when it tells you that it cannot, the type of the complex is unknown. And so when I traced it up and I realized that, okay, the new library type that has been replaced with the fundamental types was the main problem, and then we needed the fundamental type for ABI compatibility. And then there was some days of research, and then I realized that, okay, because I was trying to make the library type, I was trying to find a dirty way to make it work, but when I saw that comment, I realized that, no, maybe this could be the fix, so I just temporarily used the fundamental type there, and it worked. And I was like, okay, then let me just use an if-else for it, and then so now if you are using import C, if it's on a C file, just use the fundamental type. If it's a D file, you're free to use a complex library in the compiler. And then, so now you can have a simple C source file like this with a complex definition. We have so many things that I did in the testing on the PR, so contains so many complex testings, and then even the S7 library could now compile with import C. And then, so this is one of the newest additions we've done. Yeah. So we hope these fixes will improve your import C usage. Thank you.
All right, put your hand up if you've got a question. We do have a couple of questions from Ricky on the internet. Let's start with the bottom one first. Have you run into any C code that needs a cent or ucent, as in 128-bit integers? And what about half floats?
Yeah, ucents, and we're looking into it, I think, with Dennis. I was looking into it with Dennis, and when we tried it, we didn't know that what the state of the cent type in D was. Because I remember I was still under implementation, right? Yeah, I was still under implementation, so we halted on it. But I'm sure I would look into it again. Yeah, I'm sure I'll look into it again.
And the other question he has is, did you ever look at object file emission in DMD? This is where multiple declaration detection should be handled.
Yeah, the symbol table, I think with the first one that I did, that was the first problem I talked about. If you have like multiple declaration, the symbol table was emitting more than one symbol for the same variable or function being declared. But then, because the error was from DMD's backend, I knew that I had to fix it in DMD's backend. But then making changes in DMD's backend was not something that was health-wise advisable, so I had to make the fixes in the front end. So they work. Yeah.
Hi, thanks for the talk. I had a few questions. So it sounds like with the kind of statements, the kind of like defined statements, there's a lot of edge casing that was going on. And I could see an easy way out of this is say like, okay, D's just not going to support like these edge cases, like the self-referential declares, right? So why was the decision made to kind of support all these C features, even if they're very edge casey or maybe not used very commonly? And what's the philosophy behind that?
Okay, so D wasn't primarily supporting them, but because we want to compile C, we have to find any way to make. So if you want to roll with the bad guys, you have to become bad to roll with the bad guys. Yeah. So it was just like a temporary, but then we're making meaning out of it in D. So we're finding ways to make D meanings out of the C macros. But D does not support macros. But it's just that if we see a macro in the C source file, we find a way to relate it to a way that can be used in D. I hope you answered the question. Thanks.
I would like to also note that C library authors have no shame, and they will absolutely use those features in critical paths.
All right, do we have any more questions? Yes, Walter.
I know how difficult it is to do these changes to the compiler, so I want to congratulate you
Thank you.
on coming up with some great solutions. And I know that what you did is not easy and not simple. So, thank you.
Thank you very much. Okay. What's the question?
Yeah. As a person that touched the backend, I can totally understand your problems. Did you consider like gasoline or something?
Have I considered what?
Burning it all.
Error. Cleansing fire. Any other questions, or should we just burn everything? Burn everything! Yeah. Doesn't necessarily need to be witches. I believe everything is fine enough. All right, let's just wrap it up here. Clearly, we're all delirious from hunger. So, yeah, thank you.
All right.
And yeah, that's the morning session done. How was it today? Well, yep. All right, so straight up after lunch at 2 p.m. will be lightning talks. Yes, did you guys think of any other lightning talks for tomorrow, by the way? Come up and let me know during lunch. Otherwise, 2 p.m. back here, and in the meantime, there will be capybaras.
2-2.
Okay, welcome back from lunch. Welcome back, welcome back. Anyone? Whoa, finally! How you feeling?
Good.
Good? You ready to kick off our lightning talks?
Ready to go.
Yeah, you ready to get gonged off in about 5 minutes?
I'm ready to what?
Gets gonged off?
Yes.
Good. Because you got 5 minutes starts now.
All right. So we're gonna talking about chasing, pointer chasing. So as you may know or may not know, pointer chasing is when you load a pointer and then use that address to load the next pointer and so on. This is one of the worst things you can do for performance of your application because every time you load something, you may end up having a fault, either a TLB fault or a cache fault. And because each load depends on the previous one, there is no speculation that can happen through those faults. So you take all of them, in chain. So it's pretty bad. And we have a bunch of those in the runtime or in the way we implement stuff in D, and I have a few of them there, and I'd like to maybe try to motivate someone to get them sorted out. So first one, type ID. So for classes, we can get the type ID of the class from the object. And the way it works right now in memory is like this, right? You have the object data. It has a virtual function pointer. It has a vtable pointer as the first element. It goes to a virtual function pointer, and the first element there is the type ID, right? So what we would actually want is something like this, right? So you have the vtable pointer, points to the function pointer of the object, but then with a subtraction, you can get the type ID. So that's the kind of stuff, I would like to point out, and maybe if we can get something, if we can get them sorted out, that would be great. So another one is when we don't cast. When you don't cast is when you have like an object, for instance, as type object, study type object. You want to know if it's an A or not, like some subtype of it. So right now, the way we do that is that the type ID that is, in the virtual function pointer has itself a parent field that points to the next type ID and so on up to object. And then we chase the whole chain to verify, up to object if this is a subtype or not. What we actually want is this, where we have an array of all the parents, and we don't even need to check all the parents, right? Because we know at what depth, like if we have class A, we know how many object class A is removed from object, right? So if class A directly inherits from object, for instance, well, it's the first level. It's parent 1. If there is something between object and class A, then it's parent 2. You need to check only one. It's O of 1, constant time, less pointer chasing rather than, going through a whole linked list. Even better, if it's a final class, then we know it cannot have like subtype, right? So the type ID of the object itself has to match the final class. We don't do that. We still chase the whole chain of pointers to verify if it's a subtype, right? So those don't cast implementation, they are, like, in my opinion, not so good. And with some data generation from the compiler, we can get them sorted out. No, the GC interface. Every time we GC allocate something, we load the GC object pointer, we load the vtable, and then you load the function like GC malloc or whatever it is that actually does the job. We go through 3 pointer to do that. In our benchmark with Steve on the SimGC, we noticed that it's actually 2x slower, give or take, than just calling GC malloc directly. Like literally half the time we spend on the GC is doing that. Like that's completely, it's completely unacceptable in my opinion. Like we cannot get a 2x on something like allocating memory just because we chase bullshit pointers. Especially since like, we're not gonna switch the GC implementation at runtime. If you want to do that, like good luck. It's never gonna work. I don't even see like a word in which that is possible. So yeah, we want to like get rid of all of that, like just have the runtime called the GC malloc, and it's good. Yeah, that's pretty much all I have. So I don't know if there are questions or what, or if we have time for that.
1 minute remaining.
Okay.
And Matthias, plug in. Everyone else, we got time for 2 questions. Yeah, up on the left hand. Yeah. 2 questions. How about 1? We'll take 1. Any one? 1 question. Here we go.
Absolutely off topic, but what is wrong with your character spacing in your font?
Yeah, I don't know, but I prepared it this morning, so it was too late to figure that out.
Fair enough.
Yeah, no, it didn't need to be a good question. Do we have a good question, though? Oh, all right. Do you want to use the handheld or do you want to use the lectern mic?
I'll try this one.
All right. So we'll keep on the handheld for this one. All right. So your 5 minutes starts. Hold on. Have you
Okay.
plugged in?
Yeah,
Can we get the,
I have it here.
Yeah, here we go. Now we're going. All right. Your 5 minutes starts now.
All right, so the first thing when you want to give a talk is to decide what you want to talk about. I knew what I didn't want to talk about, which was LLM, hence the name of this talk, which is when either real engineering gives us a refreshing diversion. It's a bit of a mouthful, so you can go for something a bit shorter, which is WireGuard. Who here is familiar with WireGuard? Oh, a few, okay. So WireGuard is, it's a protocol for point-to-point communication, which you can use to set up your own VPN. It's a very simple protocol, purposely. You can find the white paper, which is 20 pages, on wireguard.com. And there's two sentences here that caught my interest. One is the simplicity and an auditable code base, and the other is a pursuit of a solid engineering solution over something, well, more technically interesting, but maybe less practical. And that sounded exactly what I wanted to do for a non-LLM task. So I set out to implement the protocol, which is fairly simple. You need your own private key, obviously, for communication, which is an ED 25519 key, and you need the public key of your peer, potentially a pre-shared key, and then endpoint address and what address you will have on your VPN. It offers a stateless UX, which is very convenient, but under the hood, it's actually stateful. You have a one round trip for a handshake and sessions that last about 3 minutes. I highly recommend reading the white paper. It's really interesting. It's a really good lesson in design. And so the implementation was fairly simple. Implementing the protocol was less than 1,000 lines of code, so small and auditable check. That was the fun part. The not so fun part is actually implementing the communication part. So you need to set up a TAN device, because the way you communicate is you take an IP packet, you nest it within a UDP packet and send that to your peer. That was around 250 lines of code, but disclaimer, there is zero security audit, so don't use this in production, please. All right, so it comes with a little demo. One thing that is quite nice to do when you implement such a protocol is just to test it against the production. So here we have my VPN. You can see this peer here, which didn't handshake for a while. And here the implementation. You run that, set up a TAN device. You can see that you have your device popping up here. And because I have metrics, you can just do a curl, and that sends a request to the server, and it's like it's a VPN, essentially. And normally you should see that. Yeah, last handshake 19 seconds ago. So we know it works. When you do a demo, always have a backup video, just in case. So what's the conclusion here? That was a little exercise for me to have fun, because I deal with LLM on a daily basis. I don't write a lot of code manually anymore. But one of the engineering principles I live by is that perfection is achieved when there's nothing left to remove. That's a quote from Saint-Exupéry. And I encourage everyone to take such a small exercise to learn a new technology. You can implement a DNS server in one afternoon. You can implement WireGuard protocol in one afternoon. And my
1 minute remains.
Conclusion is that writing code is never the bottleneck. It's always understanding the problem. Thank you. Any questions?
Yeah, questions? Well, hold on. First, we need Attila. Get your the equipment up there. And we'll take 1 or 2 questions. And again, they don't need to be good questions, as we just proved here. Anyone?
What's the adapter?
Oh, you need an adapter? Yeah, hold on. Yeah, ask a question. Who wants a question? Any question. We will take any question. And now they're all shy.
It was a very clear presentation.
Oh, we have a question, finally.
So what's the performance like? Like within how many orders of magnitude are you from the real WireGuard?
I haven't measured it. Yeah, so WireGuard is in the kernel since March 2020, version 5.6. So it's implemented at the kernel level. There's no way a user space implementation is going to beat it. So don't use it for performance. But I will measure it.
All right, thank you. Boy, are you going to do the Lexturn or the handheld? Yeah, can we get the Lexturn volume? No, we don't. Say something.
Testing 1, 2, 3.
Perfect. All right, Attila, your
Is
time
that readable?
starts
Do I
roughly
need to make it
now.
bigger? Is that readable? Do I need to make it bigger? I can't tell. It's a little bit. All right, so in my talk, I was talking about the different backends that I was writing for D, taking the front end and then feeding it to something. And this is a weird, bizarre experiment in which I have a REPL that's based on the CTFE engine. So that's literally what you get at compile time at D, but I'm running it at runtime here. And so you can do things like this, and import the standard library, which takes forever because the front end and SEM are slow. But this weird thing works. And if I don't use array, CTFE likes printing ranges like that. So that's what happens. But weirdly enough, that works. And this doesn't work, though, because, of course, compile time stuff doesn't really work at runtime, even though I'm now running it at runtime. But I have a tree walking interpreter, so import phobos again, because otherwise it doesn't have any memory of stuff, obviously. That still works and prints the same thing the CTFE does. So there's that. But now I can actually write to files. There you go. REPL for D. That was it.
Really? That was it?
Yeah.
Oh. All right, so who had a question? Okay.
I would like you to make a brief article about that and put it up on Hacker News.
Yeah, I'm waiting to actually have something that works with all code, because there's stuff they won't do, and it's super slow.
We don't care about that stuff.
Okay, fine. All right, I will, but I'd rather polish it up first. But for toy stuff like this will work. The other thing I didn't show here, actually, which was kind of dumb of me, now that I remember. Hang on.
Is this open source?
Yeah, of course.
Okay.
Wait, that's not what I wanted to do.
I would like to play with it.
Sure. So I did this thing as well, which you can pass it a dub project, and then you'll be inside of it. So that will work, because now I'm inside the dub project, so I can just play about with any dub project I want, because all of it's being interpreted, and then I can call, random functions from it. And then that serialized that integer into 4 bytes. But as if I were in the dub project, so you don't need to write code, you could just play about with whatever dub project you want, assuming, of course, the interpreter manages to handle it, but it managed to handle this, so yeah. Now I'm done.
All right, thank you again. I lost the other microphone. Where did the other microphone go? You've got it? Perfect. Do you want the Lexturn mic or a handheld? Lexturn or handheld mic?
Handheld?
Handheld. All right, yeah, I'll get that on the mic. perfectly organized here, as you can see.
Is it connected to the display now?
You will see what's being presented down there. So,
Is it HDMI?
yeah, I mean, that's an adapter for HDMI, so you can plug it out and do HDMI directly.
No, it's just visuals.
There we go. We good now?
Yeah.
Perfect. Well, we'll get the display up there, and then I will let you know when to go. All right. Hold on. And your time starts now.
Right. I want to talk about a little investigation for types as expressions, or first-class types, as some you might call it. There was this forum post this year by Per, who suggested allowing using the ternary operator for types. And Attila replied, I like it, and I like the idea, but I don't like making it a special case of alias. I would like it to be general. And it reminded me of an older discussion from Andre, who found an approach to use to re-implement std meta with iterative normal code instead of template code. And the trick is to reify and de-reify, so convert the types into strings, use those strings, and what he did was use string-off to convert each type to a string, and then manipulate strings with map, filter, just regular functions, and then convert back to mixin. Although the strings are not very hygienic, so a better approach is to use the mangle-off, which is a unique serialization of each type, and a trait was added to the compiler to convert back from mangle to an actual type that can be used in declarations. So you can actually have some kind of first-class types today. It looks like this. It just looks kind of ugly because you have to add .mangle-off and the traits when you actually want to use it. But the compiler could theoretically do a lot of that automatically. So I got, and also you can make the traits, you can wrap it in a template to make the syntax a bit better. But I had the idea, why not allow implicitly converting types when used in an expression as a mangle and give it a type T, and then allow that to be used in functions. The compiler already has to convert expressions to types in its semantic analysis, because in templates, there's ambiguous cases where it sees X indexed by Y, and only after resolving the symbols does it know if it's a static array of integers or an expression indexing an array value. So that code is already there. What isn't there is allowing pointer declarations in expressions and type constructors, but that's an easy parser change. So that could be added to allow cases like this. It helps removing the need for the is expression. You can directly compare type-of against a type, literal type like int. You don't have to add these extra parentheses, which I think is nice. And I found out that it also works pretty seamlessly with existing constructs. You can switch over type instead of having a long chain of static ifs. You can create an associative array mapping types to another, like here, going from int to uint and other unsigned conversions. This is a function from Phobos adapted how it is currently, where it uses, you give it a type and it gives implicit conversion targets. So for a short, it gives bigger integer types that it can implicitly convert to. And it lists some things and recursively instantiates more templates. And you can see a large static if chain. And with first-class types, it could look like this, which I think looks a lot better. It's more readable. You can put the types in arrays. But the big foot gun that was hidden in the code you saw before is that the .init and .sizeof properties currently, when you give them a value, they evaluate the size or init value of the type of that expression. And that can lead to ambiguity when you have type T values at CTFE.
1 minute.
That is what I got stumped on. So I wanted to share. I was like very happy, like, ooh, everything works out, minimal compiler changes, and it looks also nice. This is where I got stuck. You would intuitively think, for example, in this larger type function, that a.sizeof comparing b.sizeof will compare
like if you pass it int and short, it will compare 4 and 2. But no, this just compares the size of type T, which is like 16 if it's just a string mangle. So it will always be 16 larger than 16 and just return, the type B. And similar for element type, you specify t.init, and is it the init value of the value at CTV at that point, or the static init value of type T. You could hack around a bit, like the compiler could detect some cases, but I haven't really found something that really makes sense and doesn't result in a lot of confusion. So that's the trade-off, and that's kind of what I end on. If anyone has an idea to unblock this idea, then
All right, do we have any questions?
Awesome.
Hey, Attila, say that for the microphone for the people at home.
Awesome.
Any questions?
any solutions to my
Any
talk?
solutions?
Yeah, I think in general you cannot really do this without any sort of dependent typing, because the type of t.init would need to be, well, two type of your mangle, and that is a runtime value.
You need the adapter, don't you?
No, I don't need an adapter. I just need a quick cable.
But there's got to be something simpler than adding complete dependent typing to D, right?
Well, you could detect these cases and disallow them statically.
Right.
Any other questions, comments, solutions, general observations, situational humor, anything? Nope? All right, well, thank you again. Well, that looks like a screen at least. Hey, there we go.
Hold on a second.
Cool. Did you want the
Is that?
handheld?
Yeah, that's what I want.
Yeah,
Okay.
that'll flash up there. Do you want the
That's what I
handheld
want
or
there, yeah.
lectern mic?
I'll take the lectern mic.
Cool. Okay, we're doing the lectern mic again, and when that flashes up, I'll let you know when you're good to go. Doink, doink. Time starts now.
All right, this is going to be a quick overview of robot programming, which is something I'm involved with recently. So I am a software mentor on Team 2079, Alarm Robotics in Massachusetts. And this is kind of a little video of like our robot performing this year. The first organization has teams all over the world, all high school age students, teams in many different countries, mostly in the US, but there's quite a few in Israel as well, and some in Australia and UK. So we're all over the place, and one of the things I love about FIRST is their basic is about teaching kids the fundamentals of working together. So the two philosophies are gracious professionalism and cooperation. The former being like doing high quality work while showing respect for others and emphasizing their value. And then cooperation is showing unqualified kindness and respect in the face of fierce competition, which is something that I've seen firsthand. Basically, teams who are competing against each other help each other out, lend parts, all that stuff. It's really nice. So a quick overview of how the robotics control system works in FRC. You have a microcontroller on your robot, which is running, at this point, Java code for us. You have an initial period in the game for robot-only control, which means that the robot is running itself. There is no interaction with the human. And then after that, the students drive the robot for the rest of the time. If you look at that video, that was all robot control, so the students were not doing any of that. But we obviously write the program to do that. So, if you think about video games, basically you have an event loop, and your game runs some code every loop. And yeah, you can do like physics simulation, but it's easy to fudge physics. Like if you look at the simulation, basically if two balls collide, they're inside each other for a second, and then I just move them out. It's really easy to do in a computer, but in real life, that doesn't always work. So yeah, there's no damage if you get it wrong, but in a real robot, you're doing basically the same thing. You run some code every frame, robot frame. So it's like it's 50 hertz in this case. We read sensors, tell motors what to do, run LEDs, And obviously there's no simulation, so you have to deal with the actual physics. If a robot hits you and you get jostled around, you have to adjust for that. And there's a command system, which is essentially a little DSL that runs to allow you to run a process over multiple frames. And it's a little bit complicated to understand for the kids, but it's getting better. I think this year it's going to be a lot better. But one of the main things we use is a PID loop. I know there's a lot of people who are familiar with PID loops, but in case you aren't, it's an industry standard way to execute physical motion that takes into account real-world feedback. So if you look at this demonstration here, the bottom just has P, and then the middle one has D as well, and the top one has I. Real quick, the PID stands for proportional, where you basically take your error, where do I want to be, and where do I want to go to, and just factor that into your output, which is basically how fast to drive the motor. Integral is an accumulation of all the error that's ever happened, and that helps. So if you see the top one has the I in it, it gets a little bit closer because it has that little error, whereas the middle one kind of comes to a steady state, but not perfectly on the target. And derivative is the difference between the error. So what was the error last frame and this frame? That is kind of your velocity of error, and you add that in. So this is like the main thing that you're doing. We have like PID loops running everywhere, PID loops running in the motors. So this is like one of the most interesting things I think about robot programming. And if you're interested, I think it's a really fun time. You get to teach kids, having them understand how to do STEM and electronics. We're building things with CNC machines. It's really, really fun. And you get to write some cool code that actually does things in the real world. So look around, see if you can see if there's a team near you. You might find that really fun. That's it. Oh, and this is a picture of our team when we went to Worlds in Houston.
How do those robots perceive the environment? Do you
Okay,
have,
so yeah,
LiDARs or stuff?
So if you look, can I get my cursor over here? If you look at these little tags here, that one right there on the hub, this little tag right here that looks like a QR code, there's a system that's, you put cameras on, you say how the cameras are oriented on the robot, and it says, okay, this is where the robot thinks it is on the field to a certain degree. And you can have multiple cameras. So essentially you have eyes on the robot, but the eyes don't have to be pointed at the thing you're doing. They can kind of be pointed anywhere. And as long as it sees one tag, then it gets an approximation of where it is. So yeah, when the robot goes and grabs all these balls and stuff, see it hit the robot, it readjusted where it was because it saw that tag and said, oh, I got moved here. So even though it can tell from its wheel odometry as well. So when it turns the wheels, it's like, I think I moved this far this way. If there's no slippage, then it's pretty accurate, but it gets very inaccurate over time.
What about the shooting of balls?
The shooting that's where the PID loop comes in. So essentially we know where we are. We have a lookup table of if I'm this far away, shoot them this far, shoot them this hard. And then you have the alignment, which is based on those tags. So how do I align myself so that I can shoot? It's actually quite interesting problem to solve, and it took us a lot of time to solve it. Yeah.
Do you have any feedback if the ball goes in to adjust that, like the power with which you shoot the ball?
No, but the field is static, so we could put that in there. We could say, oh, you know what, it's a little bit off. Let's move it back a little bit. But for the most part, as long as the cameras aren't moving, and the cameras on the robot can't bounce around or anything, then it shouldn't be a problem.
And then you probably tuned the PID too.
Yeah,
so.
we tuned the shooter way beforehand. If you saw this video here, this is us testing things and seeing how far does it shoot.
So are you allowed to use cameras or some GPS stuff
So our cameras are running off of coprocessors. So you have the main processor just running the robot code, and then you have a coprocessor just running Linux, and that has a vision system in it that's hooked to the cameras. And it's basically sending back to the main robot code coordinates in 3D space of this is where the camera sees tags. I see a tag here, I see a tag here, here's the orientation. And then the robot back calculates, okay, that means I'm here on the field.
So do you see where the balls are, or do you just randomly go and hope
You
to...
can, people did do that, you know, to the balls, but for the most part, you know where the balls are gonna be, or if you, there's enough of them that if you don't, you know, if you pick up none of them, then it's okay, you know. There was a lot of scoring this year. Yes.
Hey, nice talk. Besides the computer vision, is there any kind of like higher level machine learning where like you learn different behaviors during autonomous and stuff like that?
There's a lot of that that's coming around this year. So a lot of teams were doing, so if you notice in this video here, if I can get back to it, kind of towards the end, let's see if I can get it to, where was it? Like right here. So after he comes out, he all of a sudden gets up on the balls and that's it. Like we were done at that point. Like actually we have the program goes and collects more balls and then comes back and shoots again. But because we got stuck on the balls, we just basically beached there. But some teams were making machine learning tests to see, am I stuck on balls? And if I am, do this kind of a moving thing. Because once the game starts and the kids can grab the controllers, they do get off. You know, they know how to maneuver it off. So but there was some machine learning of like, oh, I got stuck on something, so well, at least you don't want to shoot your balls out like off to the side. So that's one thing. So yeah, there is some of that involved.
All right, I think that's all the questions. Thank you. All right, we have roughly a 14-minute break before we have the next talk at 2:45. So have fun. Hello, everybody. How we doing? Yes, there's that early afternoon energy that we all love. Actually, it's getting near mid-afternoon. What am I talking about? Come on, let's have a little bit of energy. And we need energy because our next presenter is not in the room. Oh, yes, our next presenter is coming in remote from Vietnam, I believe. Yeah, and I believe it's the first time DConf presenter as well, so energy, energy. And yeah, my Vietnamese pronunciation is a bit rusty, so excuse me if I get this wrong, but it's Ha Pham Quang talking about Vulkan Compute support in DCompute, so let's hear it.
Hello. Can you hear me?
Yep.
So, good afternoon, everyone. Welcome to my presentation. This is my very first time speaking at a big conferences like this. So, because I live far away, I am joining you online today. So, please forgive me if I make any mistakes. The title of my project is Vulkan Compute Support in DCompute and LDC. But today, I will not just talk about code. I will also share my real story and the challenge I faced during Google Summer Code. Let me introduce myself. I am Phạm Quang Hà, an IT student at Federica University in Vietnam. I really enjoy learning new technology. So how did I find the Language Foundation? I saw the Language Foundation on the Google Summer Code website. I realized the language is very unique. It's fast, but also very clean to write. So I decided to study it deeply. Finally, why this Vulkan project? So to be honest, other projects were too crowded. And more importantly, writing a Vulkan backend is a very hard topic. I wanted to step out of my comfort zones and challenge my skills and learn how GPUs really work. Now, let's talk about the main question. Why did we choose Vulkan for the D language? The first reason is cross-platform support. Vulkan uses a bytecode to format called SPIR-V. Because of this, we can write our compute code once and run it everywhere. It can run on Windows, Linux, and many different systems. The second reason is freedom. You can avoid vendor logging. For example, if you use CUGA, your code can only run on NVIDIA hardware. But with Vulkan, you are free. Your code can run on AMD, Intel, or NVIDIA GPUs. You don't depend on just one company. So what is the final goal of this project? The goal is to let developers write GPU compute kernels entirely in pure D language. They don't need to write C++ or learn a new setting language after writing in pure D. They can run the kernels natively on any Vulkan hardware. Now, let's look at the compilation architecture. How does our code go from the text editor to the CPU? It happens in 3 simple steps right here. First, we start with the D source code. As a developer, you can program in normal D language to tell the system that this code is for the GPU. You just add the compute annotation. For example, you write @compute for the module and @kernel for the function. It is very easy and clean. Second, this source code goes into the LDC compiler. LDC does heavy lifting. It takes your G code and compile it. but it does not compile to normal CPU code. Instead, it compiles code into a special format called Vulkan-ready LLVM IR. Finally, we move to the last step, SPIR-V and Vulkan. We use a tool called LLVM SPIR-V translator. This tool takes the IR code and generates a .spv bytecode file. This .spv file is exactly what the Vulkan GPU understands. You just send this file to the GPU and the Vulkan hardware will execute it. Here is a quick look at the code. You can see we write it completely in purely language. You do not need to learn any complex shader language. There are two important tasks here. First, look at the top. We use as compute attribute. This tells compiler that module is for the GPU device only. Second, at kernel attribute for our main function. After writing code, the next step is compiling and execution. To compile, you only need one simple command. You can see it in the black box on the screen. We just go to LDC2 compiler and set the target to Vulkan. This command will read our D code and generate a test.spv file. After compiling, we need to execute it. We take this SPV file and load it into a runner program. For this project, I use a runner called Vulkan Minimal Compute. This runner will send our file to the GPU, run the code, and get the final result back for us. Let me show you how exactly it works. This is a video about it.
Hi everyone, welcome to the live demonstration of the dcompute Vulkan backend. In this video, I will show you how dcode compiles into SPIR-V and executes directly on a Vulkan GPU. First, let's look at vulkan_minimal_kernel.d. Here we write a pure dcompute kernel using at compute and at kernel attributes. The check lines at the top are standard LDC file check rules used to verify the generated SPIR-V assembly. Next is vulkan_vector_add.d. In this kernel, we pass multiple buffer pointers and perform parallel element-wise addition, calculating vector C as vector A plus vector B directly on the GPU. To run these shaders, we have our C++ host test runner in main.cpp. This file contains the Vulkan boilerplate to initialize the physical device, set up descriptor bindings, and dispatch the compute queue. In main_vector_add.cpp, lines 107 to 113, we initialize our input data, vector A with 1.5, 2.5, 3.5, and vector B with 10, 20, 30 before passing them to the GPU memory buffer. Now, let's execute run.bat. This batch script automates the entire process. LDC compiles the D kernel into a Vulkan 1.3 SPIR-V shader, automatically optimizes it with SPIR-V opt, and our runner executes it on the GPU. As you can see, it successfully returns 67.36. Now, let's run vector_add.bat for the vector addition test. The GPU computes the result in parallel and returns the exact expected output. Vector C equals 11.5, 22.5, and 33.5. In summary, the full end-to-end compilation pipeline, from high-level decode through the LLVM SPIR-V backend to physical GPU execution, is working successfully. However, our current testing setup still depends on an external repository called Vulkan Minimal Compute, which requires manual compilation and is not yet fully automated. Therefore, in my SAOC proposal, I propose to integrate automated GPU runtime testing directly into the LDC Lit test suite and build TensorD, a GPU accelerated tensor and machine learning library for D. Thank you so much for watching. Hi everyone, welcome.
So that was the technical part. Now I want to share my real story. As a beginner, this project was very hard. Everything was new to me. During Google Summer Code journey, I faced the four major challenges. First, the massive code base. Second, the complex build environment. Third, API and upstream book. And four, the language barrier. So let's look at the first challenge. The massive code base. LDC has hundreds of thousands of lines of C++ code. When I first saw it, I was honestly a bit shocked. To handle this, I needed a safe strategy. I did not jump into the hardest parts right away. Instead, I start small. I look for minor issue in GMT that has easy labels. Throughout this challenge, I kept on myself, learn by doing. Whenever I got stuck, I try to figure it out by myself first. I use AI to ask basic questions and understand the new concepts. But I never just copy and paste. I always make sure I understand the logic and never rely on AI too much. If I could not understand something, then I could ask my mentor, Nicholas. Nicholas was very helpful. He showed me how to narrow down the problem and taught me simple pre-debugging. And finally, after I finished my code, he would review it and help me fix any mistakes. Moving on to my second challenge, the complex build environment. For this project, we need to target the newest LLVM version. Specifically, LLVM version 2023 and 24. In software world, we can call it like junk version or something, because it is so new, it changes fast and can be hard to set up. This led to a very frustrating situation. Before I could even write a single line of my own code, the system gave me endless linker errors. The main problem was a mismatch between static and dynamic linking. The compiler could not find the right libraries to connect. It took me many days just to build the project successfully. But through this, I learned a lot. I finally understood how compilers and linker actually work together under the hood. The third challenge was fixing API tests. This was a very complex task. To fix these tests, I could not just change the LDC code. I actually have to make deep changes directly inside the LLVM code base. Because of it, I had to debug and file and fix code in both repositories at the same time. It was a lot of hard work, but during this process, a very funny and embarrassing incident happened. I call it the LLVM incident. So here is the story. While I was writing code, I left some personal notes for myself in Vietnamese. By mistake, I pushed this Vietnamese comment directly into the official LLVM upstream. I realized my mistake, so I completely panicked. I quickly tried to use a fork push to delete it and hide my mistake, but the open source community is just too fast. Before I could hide the evidence, a username Final Evolution on the D forum already saw it, and he told me this. And my mentor Nicholas Wilson also saw it. He messaged me on Discord immediately. So because they found it out so fast, I was very embarrassed at that moment. But I looking back now, it was a very funny memory that I will never forget. Finally, let's talk about my last challenge. This one was not about code, it was about communication, the language barrier. As you know, that I am from Vietnam, English is not my first language. At first, I talking about a complex technical thing in English, it felt very daunting. Because of this, I had a lot of anxiety and hesitation. I was very afraid of asking stupid questions. I worried that my people would misunderstand me or that my English were not good enough. But I have learned a very good lessons. The open source community is incredibly supportive. They were very patient and helpful to me. I realized that if we share the same passion for coding, language is not a barrier. So from all these challenges, what did I learn? First, the patience is key. Reading massive code base takes time. Second, communication is just as important as writing code. For future contributor, my advice is simple. Start small with easy issue. Do not be afraid to ask questions or make mistakes, and use AI as a tool to learn, but never use it to replace your own thinking. So let's look at the current status. What is done? We successfully add Bunkan support to FDC, and our code runs correctly on a real GPU. For the next step, I need to merge two pull requests into the FDC and LLVM repository. In the future, I plan to auto testing and build a machine learning library that called TensorD. To finish my presentation, I want to say thank you, special thanks to the Language Foundation and Google Summer Code for this amazing opportunity. And a very big thank to my mentor, Nicholas Wilson, for his great vision. So thank you everyone for listening. If you have any question, I am happy to answer now.
Well, applause first. Yeah, he can hear our microphone feed, so if we have questions, we are taking questions in the room. I'm also looking on the internet. So, any questions? Questions? Over here with John.
What can you do with, say, CUDA that you can't do with this Vulkan backend? Like, because obviously Vulkan has this compute capability in it, but are there limitations that make it less good for some tasks?
Can you speak? Can you ask me again?
So,
slowly.
Okay. What limitations are there on using Vulkan instead of CUDA or some other equivalent?
So you ask me what limitations are there on using Vulkan or using Vulkan instead to TI or what?
Yes.
No. To be honest, I haven't explored that part. But I will look into it.
Cool. Any other questions? Okay, going. Oh, there we go. Mike's up the back with a question.
Yeah, just wanted to briefly thank you for the presentation and comment that the videos and those tutorials that you made were going to be really helpful for others as well. So thank you.
Yes, thank you.
Yeah, let's get applause again. Thank you. All right, so we got a bit of time until the next talk. It's 3:45, so be merry, do your thing, and back here in 33 and a half minutes. All right, are we all rested? Are we all had our thirst quenched? Are we all alive? Let's hear a sign of life here. Well, this little bit in the middle here appears to be alive. I'm a little bit less convinced about the parts and the sides. Can we have a bit of sign of life from everyone, please? There we go. And keep it going because we've got a first-time DConf speaker. Azad, I already broke your name. Azad Beck, sorry. Take it away.
Hello, mic test, okay, it's working. So my presentation is about similar project like Juan did. He did for Vulkan GPU target. I did for Apple's Metal GPU. Has anybody heard about DCompute? Like, cool. Has anybody done any GPU programming, like in D or outside D? Cool. So we have some context. So in my presentation, firstly, I am going to talk about the current state of DCompute and the compilation steps, and then challenges I faced while adding support for Apple GPUs. And we'll go over small details about implementation details, and I will show working demo of image convolution in Metal GPUs. So current state of D, you can write compute kernels. Kernels is basically a function that will be executed on GPU. And it can be all written in D. And we will compile the DCompute kernels using LDC compiler and DCompute standard library. And we can lower to NVIDIA PTX and execute compute workloads on NVIDIA GPUs. And also, we can emit SPIR-V and using OpenCL, we can execute OpenCL capable GPUs. And now, with the project I worked on, I have added support for Metal GPUs, and we can now have access to Apple GPUs, all natively in D. So before going further, let's see what is the basic hello world example can be in DCompute. So GPU hello world program is just adding element-wise sum of two arrays elements and writing the output to third array. So as you can see, there is this vector add function. It accepts 3 arrays, and it just gets the magic index from GPU and from GPU library. And in our case, it's DCompute. It just gets the index and just writes the sum of 2 elements into the third array. So here is how it looks like from host program to device code. You don't have to understand this code. It's just there to show that it works fine from host to device codes. Currently, we can, in LDC, we have support for major targets in CPUs. And with DCompute, we can now target to CUDA and OpenCL. Through OpenCL, we can target to various GPU devices as well. But yeah, with DCompute runtime, it has bindings for that can talk with GPU devices. So it has bindings for CUDA, it has bindings for OpenCL. Now I added bindings for Metal API, so it can talk to these devices now. And combine it with the DCompute runtime, the binary that will be generated from LDC, that is device specific. We can run compute workloads all on D. Yeah, so we can run everything in D, and it's all working. Challenges I faced is, as you can see, the project scope is really big. There are lots of moving parts. I have to update things on LDC compiler and also do some work on host side. And by host side, it's the DCompute runtime that should talk to Metal devices. So Another challenge was differences between the device APIs. For instance, as you can see, CUDA is on the left side. You can see how CUDA can be written to express the same function, vector add, and in the middle, OpenCL, and on the right side, it's the metal shading language. The differences are, as you can see, we should specify the buffer index on the arguments explicitly, and also we should specify additional argument that represents the thread position in the grid. That's the GPU-specific intrinsics. Actually, that's how we can get the thread index from GPUs. So I will talk about how I have done this metadata mappings for metal shading language to decompute without changing anything on the front-end side. So you can basically define one function and run on various GPU devices without changing anything. So another challenge is Apple maintains its own LLVM, and they don't open source it, they don't document it. So it causes major problems. And another one is Apple's LLVM is older version of LLVM where it emits bitcode that is of older LLVM version, so it causes backwards compatibility issues. So I will also talk about how we can resolve this. Firstly, I started my work with adding Metal API bindings to decompute library that allowed me to talk to Metal GPU devices without adding compiler work. And I slowly added compiler side of changes. So I told that Apple maintains its own LLVM version. The challenge is they changed the LLVM and they require special metadata emission to specify this function is a kernel and this function is a vertex function or any GPU side of function. So I had to emit such special metadata, and I had to reverse engineer which metadata, how the metadata should be. So I had to play around with metal shading language kernels and emit LLVM IR and check how it encodes metadata to represent the arguments and stuff like that. And so at the end, we generate metal.metallib library. It's one of the binary files. We just specify the path to this binary and send this to GPU driver. And decompute follows the same interface, like message passing interface, as how it's done in Objective-C or Swift or OpenCL. So we just follow the same principles. The first work I did for a compiler is I had to configure the new decompute target for Metal GPUs, and I had to emit Metal GPU compatible LLVM IR with special metadata. And then, as I mentioned, Apple maintains its own older version LLVM. So we had to emit LLVM bitcode that is expected by Apple LLVM bitcode readers. So LLVM bitcode writer is not backwards compatible, but LLVM reader is backwards compatible. LLVM reader can read older versions of LLVM bitcode, but it cannot. LLVM bitcode writer cannot generate older versions of LLVM bitcode. So I had to use utility tool that downgrades LLVM IR bitcode, basically. And then on the host side, I added Metal API bindings to decompute to be able to talk to GPU device. Here is how I define a new decompute target. The special things that everybody should pay attention to is how address spaces are mapped. So in GPU, there are different levels of address spaces. There is device level address space, constant memory, or private memory, or thread group memory. Yeah. And also, there is this special target triple that I had to hard code because current upstream LLVM doesn't have official Apple target triple, so I had to hard code that. Also, in the host side, I had to add abstractions because the compute is heterogeneous computing library where you can just define one function and be able to run this function on various different devices, GPU devices. So I wrapped this. I used LDC intrinsic pragma. It's a special attribute that is LDC specific. And I just used these intrinsics on the compute library. And here is the differences. Like I had to hard code this target triple, and I had to add this AIR.kernel. It means Apple IR, or Apple intermediate representation kernel, that specifically defines what is kernel, or what is compute kernel, what is vertex kernel. So for compute kernels, it's called kernel. And as you can see, it just references to vector add. And the way arguments are specified is also in the metadata. So that starts with 0 and 1, and yeah, follows in this structure. And here is the diagram of how Metal API looks like. We follow the exact same paradigm as message passing interface in dcompute. So yeah, now it's time to demo. Let me show you how we can run image convolution. Everything will be in decode and will be on my Mac device. I hope you can see my screen. I will zoom in a bit. So I defined this function as image convolution requires filter matrix to be defined. So I defined this matrix, and I just gave the equal weights for this matrix elements. Yeah. And in the kernel side, here is how you can define kernels. You should use a special kernel attribute. And then here is how arguments looks like. This global pointer, it represents device level memory. I mentioned that there is address spaces. Global pointer in dcompute, it represents device memory. And for Metal targets, just scalar values will be stored in constant memory. So yeah, let me show you how we can run this. So here is my dub JSON looks like, how my dub JSON looks like. I have prepared 3 demos. So I will run the first one. Yeah, I use my local LDC fork. So yeah, firstly, let me delete the existing one. So that's the image, and we will blur this image using image convolution algorithm. Yeah, it wrote the image. So as you can see, it's blurred out. So that's the first example, and that's naive approach to define this image convolution. I tried to optimize that using LDCs or these core SIMD float for type. So in the loop, this sum is floating point for number. So it has the addition on 4 lanes, basically. So let me run the demo 2. Oh, I forgot to delete this. Yeah. Okay, it worked. So, yeah. Oh, we forgot to measure the performance, right? Technically, floating point for vectorized implementation should be faster. Let's measure this. Firstly, let me generate executable for the first example, and I was able to. So yesterday, I thought, what if we can? What happens if we can debug this generated metal library? So I was not able to make it. I was not able to make debugging work, but I was able to generate traces so that we can see how performance works, how performance turned out to be. So let's generate demo. Let's generate traces for demo 1. Okay. Let's open the demo 1 trace. Yeah, compute-wise, it took 11.75 milliseconds. Let's test how vectorized implementation performs. So I just need to compile it and get the executable. And let me generate traces for the second demo. Let's open traces for demo second. Okay. Well, it took 9.2 milliseconds. It's faster. And the third demo is about how we can interface existing metal shading existing kernels that are written in metal shading language, because there are some programs that we cannot express in dcompute. So for such programs, it's we have good and not boilerplate interface in dcompute on the host side. So we can use the same host side code for the same exact implementation in metal shading language. Firstly, we just need to compile this metal shading kernel. So let me compile that, and so it generated this LLVM bitcode, and we just need to specify the path to this bitcode, and just run dab once more on the third demo. Oh, again, I forgot something. It should have worked. It worked before the demo. Yeah, it's. Let me check quickly, and yeah, I'm sure it should have worked. Okay, it says it cannot find this kernel. Let me check if the kernel name matches. Yeah, it matches. Let me try once more. Okay. Yeah, it was an experiment. I just added this metal shading language kernel just before a couple of hours before the demo. It works fine, but at this stage, I'm not sure why it didn't work. It should have worked. Yeah. So let me get back to my slides. So we talked about how, current state of dcompute and how it can compile native decode into GPU-compatible binaries and execute things on the GPU. And we talked about challenges and differences between dcompute and other GPU compiler codes. And we talked about how we can overcome, how I overcome these challenges, and did a small demo. So thank you. I need to I acknowledge that Nicholas Wilson was really helpful, and he take up his time to review my PRs and answer my stupid questions about LDC. So thanks to him. Yeah.
All right, now it's question time. Raise them if you got him.
So this uses a graphics card on Apple. I know they have a neural engine thing. Does this sort of fall out for free because we're using the existing compilation architecture for that, or is that still something that has to be done manually?
Like which part?
Like if we're doing, if you have a kernel that does it just use the graphics card, or does it also use the like neural accelerator stuff for?
Currently, it only supports what you can do with metal shading language. You can do basic stuff currently. Like you can, I have seen other compilers trying out tensor cores. You can technically do that in D as well. We just need to, or we just need to add metadata like I showed you. So for vertex functions, there is special metadata that is AIR.vertex, and for tensor functions, probably there is such metadata. I haven't checked tensor cores, but yeah, it is possible, but it was outside the scope of my project. Yeah.
So I was, thank you for your talk, by the way, very interesting. I was in, you showed how you used SIMD, like the float 4 type, to improve the speed. And my high-level understanding of these GPU languages is that you don't know which GPU it's going to run on, and they have their own idea of what like the optimal batch size and everything is.
Yeah, I haven't showed. I mean, there is batch sizes. So we can definitely fine-tune these batch sizes. For instance, I really forgot to show this. It's easier to show it in the demo 1. So Q.NQ is basically where we invoke these image convolution functions. And as you can see, there are 2 dimensions that we define, global and local dimensions. The image I gave is 512 to 512 pixels. So as you can see, global dimension, it represents width and height. And GPU grids usually are 3 dimensions. And as you can see, I defined width and height. So it means we are going to use 512 to 512 threads in GPU. Mm-hmm. And then in the local dimension, it represents how we split up the threads or work items in the GPU. For instance, 4 by 16 means for every 16 group, we have four threads in the X dimension, and we have, for every global matrix, we have 4 threads in the X dimension and 16 threads in the Y dimension. We group them by 4 and 16 threads. Yeah, we can change that and execute it again. Probably it influences the performance of the kernel. Yeah.
Right, but that's the kernel size, right? But the import core.simd and using the float 4 type, is that a separate thing?
No.
Is that just influencing the kernel size? Because I thought that's like a SIMD type is just for a single operation that it does like 4 float multiplies in one.
Yeah, one pixel has 4 elements. I will show you the kernel, first kernel, because it's easy to see how SIMD can affect the performance. We have nested for loops, and as you can see, I do 4 additions. So it does these additions at once, basically.
Right, but can you scroll up to the float 4 type? Can you?
Yeah. This is the naive approach, and the following is the float 4 approach. Yeah, it's just one sum, one number, and
so you define float 4 sum there.
Yeah.
So how do you? Is it just assumed that it's available? Like, can you use float 8, float 16? Is there, because you normally on the CPU side you target a certain instruction set, and different processors support different sizes of SIMD vectors. But for GPUs, how do you know which size your GPU supports? It will automatically rewrite it back to like smaller vectors if you go to higher, or is it just known that every GPU supports float 4, so you can use that?
In Metal, I believe there are 32 SIMD groups in one. So threads can be broken into thread groups, and in the thread groups, you can still have another groups. It's SIMD groups in Metal GPUs, and in I believe in CUDA, I think it's warp. So you can do floating point for about 32 elements, I guess, with this direction, I guess.
All right.
But it should be, like, in this case, it's only 4 elements. If it was 8 elements, I guess floating point 8 type might have been worked, yeah.
All right, do we have any more questions? Good, bad, any questions? Nope, no, I think you're off the hook there, so thank you again.
Yeah, thank you.
Okay, we have one more break for the afternoon before our final talk, and that'll be in about 33 minutes, so you've got about that long. Hello, everybody. Hello, how we doing? No, we're not even paying attention to that. Hello, how are we doing? Hey. Last talk of the day. You getting ready for DConf afterwards? There's not... DConf, yeah, there's no actual official event tonight, so after we've all eaten, you know, the Travel Lodge, we'll all just rock up there and do what we normally do. I think I do need to test everybody's age, though. Razvan, can you do me a favor and look at your microphone there and tell me what number you see on the bottom of that?
7.
7. Yeah, I got a 6 here. 6, 7. Good. You're all over the age of 10. That's good enough. All right. So we have a first-time DConf speaker here. Certainly no stranger, though. Look at this guy, Sergey. He's everywhere in the community, right? Yeah. So let's give him a round of applause, and here's your clicker.
Thank you. Okay. Hello, everyone. Hope you are enjoying DConf. So the last talk of the second day would be very chill and simple, almost no code and no technical details, no crazy templates. Sorry if somebody was expecting about it. But I still believe that this topic is important, and the main target audience for the talk is actually the newcomers or even folks who are not using D yet. So my name is Sergey Ginatulin. Some of you may know me as Serg Gini, non-official D Discord community manager. And through the talk, we will talk about how users could discover D, how they could start using it and grow their experience in D and in software development in general, how they could interact with community, start learning from community, and of course, we will see some examples of the real problems solved with D. I've also prepared several flashcards. They are not essential for the main story, but I just wanted to take this opportunity to share some attention for appreciation with the community. So if you would like to stick with one simple idea from this talk, I would recommend you to stick with this. It's not even related directly to D, and you may find this idea with different names, but if you will think about it, they all about the same. And the novelty that I would propose here, highlighted with red, and I would formulate it like, you never know, just give it a try. Of course, D has a lot of stories behind of people, how they started using D, how they continue working on compiler itself. Some of them are even maintaining their own fork now. But this talk would be about a single story, and this would be my story of the adoption of D. To start with the story, I have to share some context of my background. I've graduated from Moscow State University on a straight program of the mix of computer science and math. And even though we studied several programming languages, I've never worked as a professional software developer. And after graduation, I spent some time in academia doing some high-performance computing with Fortran and ocean modeling. And even though we're writing code, the scientific computing is pretty different from normal software engineering. You are mostly transforming mathematical formulas into the code. At some point, I found this very nice and very popular course at Coursera from Andrew and G, and I found this very nice topic. I'd like to do this stuff. At that period of time, Python was not dominating in this field, and we were doing this course in Octave, which is an open source MATLAB version. A nice time. And I decided to make a switch from my PhD program, and I joined industry as a data analyst and risk manager in the banking area. So we are mostly, you can see the tools which most of us are using at the day job. So even though we are writing code, but again, this code is pretty different from software development. You are mostly wrangling the data, cleaning the data, and then trying to build some models and validate them. and of course, spent some time on this industry, but I always like to learn. And right before the COVID, I've joined 1.5 year extra educational program from local IT giant in data science. And because of the students in this program had very different backgrounds. Some of them were university students, some data analysts, and some of them are even software developer with more than 20 years experience. They've added the classical data structures and algorithms course of the first semester. And I've started doing this. The course had 2 streams, the data science stream and machine learning engineers. So we had these 2 languages dominating in the course. And I speak Python because I already was familiar with this language. And we had no exams in this course, but we had to do our homeworks every week. And we were using Codeforces platform. So if somebody doesn't know, Codeforces is one of the famous platforms for competitive programming. And competitive programming is when you have to solve a bunch of problems in a limited time, but you also have several constraints. So you can see on the slides, they have usually 2 constraints, like time limit and memory limit. It would be important because I started doing this homeworks in Python, but one day our host and teacher presented the problem that was literally impossible to solve with Python. Even if you implement the proper data structure and algorithm complexity, the constraints were too tight. And to be honest, at this point, I was already thinking to switch the language because I found the Python too high level to implement the data structures and low-level stuff. Like Python doesn't have arrays. You need to simulate kind of allocations. And I just found it not right to use it. So I considered 2 languages because I already know C#, but I was never a big fan of C# because of large runtime and the whole verbosity of the language. And of course, the second obvious option probably was C++. I had some experience with C++ in university, and it was before C++ 11, so it was so bad. I prefer never use C++ anymore. So it was a course, like the study course about deep learning neural networks, and somehow I found this article. So a well-known company presented the new neural network framework, and they were saying that, we implemented this new framework in D-Lang. What is a D-Lang? I've never heard about it. So they said that offers Python-like experience and C++-like performance. And look, this is what I needed, right? This is what I'm looking for. So looking back in time, I think it was pretty crazy decision because I had to deliver all these homeworks every week. And I've never worked with this language. I never heard of it. But I decided to give it a try. And the crucial part was that Codeforces had the support, because otherwise, probably I won't be here today. Yeah, the time for the first appreciation. So Codeforces has different grades, and the largest grades is the legendary Grandmaster. And this user, actually the lady from Japan, is a truly legendary because she's using D on the high top level. Like most of the Grandmasters are using C++. So I started working with D on this algorithms and data structures course, but I didn't have time to properly learn D. I need to do my homework every week. So I've checked the tour, and I've joined our local community on Telegram. This was my first message in the community. But of course, if you are not in a rush, I recommend you to do it properly. You can start with Ali's book and maybe then check YouTube channel of Mike. It has a nice introduction to the D features. But unfortunately, I didn't have this ability, and I decided to just check some documentation, official documentation, and picked parts that I needed. So mostly to solve most of the problems from the classical data structure course, all you need is arrays, some containers, and ranges. And of course, I/O, but okay, it's obvious. it should be enough for you to finish the course. And ability to write code fast saved me a lot of time. And it was really awesome. And I think it saved me much more time, even though I had to learn new things while I am working on my homeworks. It saved me much more time if I had chosen C++ instead. So I successfully finished the course, and my co-students prepared the statistics. Of course, it's not robust statistics, but the interesting point is the second column of the top table. It's showing number of submissions, wrong submissions, before the user successfully solved the problem, the task of the code forces. And you can see that the D number is much lower than anything else. I think the elegance of D and the clear syntax. Of course, definitely I was not the greatest developer on the course, but it helped me to solve all stories, like all problems with the least number of submissions. But if you remember, you never know. So after this subject, I didn't have ability to use D, so we continued doing some Python, hardcore machine learning, and deep learning stuff. But for the final project, we decided to do graph analysis. So we scrapped a lot of data from some social networks, like more than 100 gigabytes of data, hundreds of thousands JSON files. And we prepared the Python script and some analysis scripts based on the Python libraries. But when we started applying this solution to the whole data set, we faced with just the performance issue. We never were able to wait the Python to read all the data. And another issue was that all 4 members of our team knew only Python. And I said, oh, look, I've learned this new cool language. Let me port it, our script for it. So what we need to do, we need to create adjacency matrix, like it's a graph representation. I've just added a parallel on for each, and we've successfully read the whole data in 30 minutes on a regular laptop. So it was the second success in just one course. At this point, we suppose that you already know the language, you're already familiar with some parts of the standard library, and you want to continue using it. So I would suggest you to start with small problems with some existing solutions. It should be easier to adopt the new language and to try to solve them easier. Of course, it would be good if you will find the patient task which you would like to work on. Some of the potential examples could be is a popular project which is called like Dingband's popular approach. When you have the broken program and you need to fix it, we have this in D. Or you may find a book with some examples in other languages, and you may try to port it to D to become a better D developer. But for myself, I found more interesting to participate in benchmarks. Of course, I know that doing proper benchmarks is a hard task. And by the way, the example on the slide is not an example of a good benchmark. But I know that some people are also skeptical about benchmarks, but I found them very useful for the learning purposes, because you already usually have several implementations, and you have some ideas, and you can just adopt these ideas to your new language that you want to work with. And numbers in the benchmarks usually are not really important. What's important that benchmarks are usually covering different topics and ideas of the programming, and you may be able to work on some stuff that you never worked before. So some benchmarks also would allow you to use third-party libraries. So at this point, you may start exploring the ecosystem as well, not only standard library. So some examples of benchmarks, like over time, I think I've participated in more than 20 benchmarks. I don't know, maybe even more. Some of them are computationally intensive, and these kind of benchmarks would allow you to learn some tricky compiler flags that would give you the most performance of your code, even though the code is simple itself. Others are covering like bit operations, and the problem itself is not that important is just an invitation to deep dive into the specific topic. For example, this happened with SIMD. Even though I worked with a parallel programming before, in Fortran I was using OpenMP and MPI, but SIMD is was a new thing for me. I've never worked with this before. And this benchmark and the great into intrinsic library allowed us to allow D shine in this benchmark. I've also tried other benchmarks. For example, this regex showed me that in the standard library, we have two implementations for regex engine, actually. One is runtime, and the second one is compile time. And it was the first time when I found out that the D has compile time, thinking that, so what is it? Like, how I can work with it? So I started diving in this compile time stuff and to find out like how I can use it. Also, you may find out when you're doing some benchmark that even official Google GitHub is hosting some D library. It's not affiliated officially with D, but probably some employer just added it there. And when I've tried to use this library, I found one issue or a bug in the library. So I've contacted the repo author, and he fixed it. So the point here that at some point, you not only exploring the language and the ecosystem, you are starting improving it as well. And which may be even more important, you may find some bugs in libraries, or some libraries could lack of documentation, or documentation may be not very clear. And at this point, it's really important to start, I think, interact with community. Because when you're starting asking library authors, you can learn so many things from them. And the D community is full of outstanding people, and they're happy to share their knowledge. They're happy to help you with any issue that you have. For example, the only thing that I knew about web development was some basics HTML from school, but then I started participating in some web benchmarks because I was curious how D would behave in this domain. And I found out that D is doing very well. So it's on par with well-known web frameworks. And the participation in the benchmarks could even help you dive deeper. So I've then prepared my own benchmarks, D-specific, which are covering not only web server, but also other aspects of web development, like clients and WebSockets. By the way, this D-server implement repo, I think, has all available D web frameworks we have. If I'm missing something, just ping me, and we will add your solution there as well. And you can even work with more specific stuff. Some web developers that I know never worked with GraphQL, and me neither, before I decided to try to add this solution to this implementation. So with but small effort, you can dive into this topic to find out what kind of library is it, which problems this library is trying to solve. I spent some time in discussions in our Discord with web server library authors, and I learned a lot from them. And I think this is a great opportunity to learn stuff, and because most of them are great experts in their areas. So to finish with the benchmark, one more example. I found this benchmark, it's data-related benchmark, where you have to extract top N records from the large JSON file. So I've prepared initial implementation and shared with community. Somehow D was the best solution at that time. And with the help from community, we've prepared also concurrent version. But the benchmark was not finished yet. So over time, other communities, other languages, people from other languages proposing new ideas, new implementations, and new optimizations. And at some point, these slipped from the top place. But I remember that one of the members of our D community contacted me, and we started working together on the second version. And it was Bruce Kernel, who is a world-class expert in code optimizations. So with Bruce algorithms, and I helped him with some testing and experiments, we saved D the first spot. So even now, I think I've made this screenshot last week. I think D is still unbeaten. So the main point here is not in the numbers itself, but that working with community allow you to interact with the great experts, with the world-class experts, but we have a lot in our community. But before you go wild and start working on your own projects, I propose you to make another stop and to spend some time on ports and bindings. Because before, what we're working on, like benchmarks and some competitive programming, you may solve these problems with a very short not number of lines. It could be just one function or a single class. But to work on the final projects, like real projects or libraries, you also need to think about the project structure. You need to think about architecture, design, some API. And I think it's much easier to adopt this knowledge when you already see the final project in another language and you just try to port it to your language, which you are interested in. And of course, the easiest way, I think this is the easiest way to learn. And yeah, because other authors already thought about these design choices, so you don't need to. So some examples that I've prepared, which allows me to deeper understand and explore the ecosystem. For example, this simple tool for working, like just splitting files into separate folders of specified size, allows me to explore several libraries in the ecosystem, which are helping you to build the CLI tools. So we have several of them. They have pretty different API. So if you just try them, you can choose one that you prefer. Another example was a bigger project. It was working with the time zones, and I had to also work with protobuf library. The interesting part here that to create this project, I had to prepare some structure of the project and prepare a separate sub-package, which was working with geometry, polygons, like processing. And it was pretty interesting as well. Yeah, speaking about dates, I highly recommend everybody to participate in this project. It's kind of advent of code, but for dates and Unicode. I did some solutions in D for this, and I found several flaws and design issues in the current Phobos implementation. So if you would think on improvement of user experience in the Phobos 3, I highly recommend you to try to solve the new version of the Phobos with this project. And the author of the project also is a member of the community. Let me maybe skip this because I don't have a lot of time. Yeah, speaking about sometimes you will need to work also with C libraries. Even though D has a decent ecosystem, sometimes you just want to use C. And I highly recommend you to try to prepare some bindings by yourself, even though you don't need specific bindings now, just to find out how is it working. So when I found an announcement that D now has import C, I decided to try to port several libraries that I was interested in. So if you remember, I was interested in graph. So this graph library has C API, and somehow it worked from the first try, even though at that period, import C had some issues. If you remember, you had to run the pre-processing first and then to add some flags to make it work. Over time, the quality of the library improved significantly, so now all you need is just to prepare some DAP file, and it would create for you the bindings. And this will allow you to know the limitations of the language and the libraries, and to have a higher confidence in the language itself and the ecosystem. You would know what you can do with it. Some ports could be pretty tough to prepare. You need to be aware of it. So I found this research repository in GitHub about sorting algorithms. So Rust guys are doing some research how they could improve sorting algorithms, and I decided to port one. And this was pretty complicated algorithm, so I had to use some debugging for this to make it work indeed, to be sure that the implementation is correct. Thankfully, when I started using D, I was using VS Code, and our VS Code tools maintainer, WebFreak, helped me to configure LLDB. Then I switched to that editor, and now it's my main editor. The cool part about that it supports Rust out of the box, so I would be able to run and debug the Rust implementation in that. But with this LLDB help, I've managed to make debugger in Z work in D as well. So the Z introduced debugger, I think, last year. So it helped me a lot to successfully port this sorting algorithm to D. So after this step, you already know the language, the standard library, you explored the ecosystem, you know how to interact with the community, and now I think you can start working on your personal projects and do everything you want. So I've just shared a couple of mine. So I've participated last year in the Advent of Code, and it was the first year when I was able to solve all the Advent of Code issues in D. And all the previous learnings I started paying back. Because, for example, for this day, I found out that the implementation that I had was the shortest that I found online, like publicly available. Probably the trick was in the transposed that we have in the standard library. Maybe other languages don't have it, I don't know. But it was really elegant solution for this day. For another day, I didn't have time to properly implement the data structures that was required to have, but I realized that actually I can solve this problem if I'm going to use the graph library. Oh, wait, I have my own graph bindings, right? So at least these bindings were helpful for myself. And using these bindings, I was able to solve this day. Do you remember this plot from the beginning of the talk? I didn't find any better solution for plotting in the ecosystem. So again, I've used my Pluto VG bindings. When I did them, these bindings, I was just curious how to properly implement import C with DAP. I didn't need Pluto VG at that time, but it helped me later. Of course, games and graphics is a great topic for D development. I think the D is one of the great solutions for this part. We have a lot of solutions and standard libraries like RayLeap, or you can use more specific libraries like HyperImagine or Perrin. You can do graphical user interface in desktop, like I'm building my own photo management small tool with a sitter. I think it's a very nice GUI library. You remember I have no idea how web development is working, but now with all this experience, I managed to build the web application for Meetup management. It's still work in progress, but hopefully it will be released soon, and maybe even next BeerConf, we can use it for the BeerConf. And of course, for my main domain knowledge is in machine learning. Maybe I wanted to share just one example is this CHDB. So if you know what's DuckDB and if you know what's ClickHouse, and if you combine them, you will know what's CHDB. So it's in-memory OLAP database, which allow you to run analytical queries very fast. It can process gigabytes of data in seconds on regular machine. Another picture from the beginning of the slides, it's a real billboard with an advertisement for Python library near my university. The CatBoost is a very popular machine learning library which provides a boosting algorithm. And the cool part of this library is that it allows you to run the model inside of the ClickHouse because both projects have some similar roots. So what I did in my test is I combined these two ideas. So now, with this example, you can read the data with CHDB, and then you can apply the CatBoost model directly in the same memory. It should be very efficient. One more thing. Initially, I didn't plan to add these slides, but I decided to add them because recently I started seeing these conversations a lot. So it's about AI. So 2 questions I've seen in the web, like why bother to learn any programming because AI will do everything for us. And the second one is, okay, if we need to choose one programming language, why don't we just stick with Python because AI is fluent in Python? So answering on the first one, the last week, I'm not sure if you're aware, there was a stealth mode for this model, which was freely available to everybody. And I spent a couple of billion tokens because it was free. So I asked the model to implement 2 projects. The first one is KeyDL binding for D, and it did very well. So KeyDL is a new format similar to SDL, what we're using in DAP. But the second project I've asked to do is a SymGC. So this is a new GC for D that we have, but unfortunately, this new GC doesn't support macOS. And the macOS and M machine is my main machine. So I've asked AI, this particular model, to port SymGC to macOS, and it failed. So the main point here, as my math teacher in school told us, that the right question is the 50% of the answer. And to know how to ask the right questions, you need to get all this knowledge with all this experience, and usually probably with all this example that I've showed you before. Speaking about the language, which language would you choose for AI era? Recently, again, in the industry, it seems companies are trying to adopt the idea that we need to adopt the language to stay relevant in AI era. So this one example showed how the Haskell user, like the commercial product, they've used Haskell for 7 years, but then they decided that the Haskell has not proper direction, and it's not allow them to stay relevant in AI era. So they decided to swap to Python. Of course, other vendors saying that their language is the best language to use with AI. Of course, Rust is always the best. But what about D? I think a couple of people before in other presentations mentioned it. I think that D already has a nice baseline to be relevant in AI era. We have built-in unit tests, types, fast compile time. D is very nice for prototyping and MVP. And I think it's a nice choice for AI, but maybe we need something more. And if somebody is thinking about the next blog post, I think it's a great topic to cover. So let's try to recap everything. First of all, for the new users, for newcomers, you need to discover that D exists. Thankfully, if you're watching this video, you already did this step. Then you need to learn the language, the basic syntax, start with the small problems, explore the ecosystem, start to interact with community, learn from community, and spend some time on ports and bindings, because I think this skill would be useful for your future. And yeah, after that, just build whatever you want, even if you want with AI. And recapping for community itself, I think it's very important that official resources should be available. They should always work, because newcomers, this is what they're going to search for. And this is the way how they will interact with the language. This is the first step for them to the language. Of course, the platforms. I'm here today because Codeforces had support for D, but Codeforces is not the only platform which is doing this stuff. There are some others of them. Some of them have D support, but it's limited. Some D versions could be outdated, so maybe we as community can try to improve the situation. Of course, be loud. If you're doing great stuff with D, and especially if you're a company, just let people know, because this could allow to bring more D people to the community. I think momentum is important. If you find a hot topic at Reddit or Hacker News or anywhere else, I highly suggest you to participate at this particular time because it would be much more fun and you can get much more knowledge of it when everybody are sharing their ideas and sharing their knowledge. And yeah, the last point is be curious. Remember about 80-20 rule? It could be very easy for you to try something new. For example, I had one day had a lunch and I found that Mojo people showed the benchmark on Unicode, how they implementing these two popular functions, to lower and to upper on different languages. And it took me maybe 20 or 15 minutes to add this solution, just clone the code, add the D solution, fix the Python plotting script, and it's done. So I've shared the results with the D community, and one of the core members of our D community, Ricky, who is working on Unicode, after maybe 20 minutes looking at this image, said, wait a minute, something wrong with these numbers. It shouldn't behave like this. Like in 1 hour, he prepared some solution that's significantly improving the performance, and just in 2 days, it was merged and helped to improve the language, because you never know. Just give it a try. Thank you.
All right, questions time. Raise them down there.
So it's a bit more of a remark than a question, but you mentioned the SimGC. It turns out that the 2% who made it are like Steven and myself. And as you can see in front of us, we have those those laptops with some fruit on them. Yeah, I would like it very much if the SimGC was working on those.
All right, do we have any questions or even more remarks? Nothing? Really? I mean, I know DConf is coming, but come on. First time talker, man. Give him a few more questions. Here we go.
What happened when you tried to, like, how did it go wrong when you set a model off to make SimGC work on macOS?
So it implemented several tests, but it found out that it had some leaks. And the problem that macOS has 16K pages, while the current implementation supports only 4K. So probably AI didn't figure out how to solve this.
Anyone else?
I have a question, like here.
Okay.
Yeah. So for, let's say, students or young programmers that just, go to university and maybe they study like these conventional languages, and how or what would you tell them if you suggested that they use D and they would say, like, why should I learn D? Like, I can use C, C++. Coding is going to disappear anyway. I'm just going to vibe code everything. So what's the point?
So I think, yeah, it was covered that with this AI, like, first of all, you cannot solve everything. And the second point, like, if the person likes to write C and C++, what can we do? But, I think the main point would just give it a try, just to check the language, to search what it can do, the ability just to compare the syntax, even the syntax of C++ and D with some features. I think for me it was enough, to switch to D.
All right, do we have any more questions? Just one more. Not even seeing a question on the internet here, so good question, bad question, random question, any question? Nothing? Oh, here we go.
I know that you commonly on the Discord promote Python as the greatest language. I'm wondering if you have any second thoughts about that.
Yeah, Yeah, you know, Python is a great language for some use cases, and unfortunately, maybe, or fortunately, it's the only available option for many tasks, especially in this AI area. I had some ideas how we can increase the usage of D in machine learning area, but it still need to work on many libraries to make it happen.
All right. Any more? No. I think we've gotten all we can get out of this audience. Okay, well, thank you.
Thank you.
All right, and that's the wrapping it up for the second day of DConf 2026. Yeah, what do you all think of today? Good, bad, ugly? Yeah, it was not a very enthusiastic good there. The internet's got to hear it. What did you think? Yeah, no, that was like a Monty Python sketch. What did you all think? Yeah, you know. All right, whatever. Yeah, so here bright and early tomorrow, we still need some lightning talks. So while you're all out drinking all your beers and doing whatever you do in an evening, please think of a few more. We need 3 or 4 more talks, and then we'll be good. Otherwise, that's it for the day. See you all tomorrow.